Hello, good morning.
மார்னிங் சார்.
சார் 10 மணிக்கு ஸ்டார்ட் ஆகுதா 9க்கா சார்?
ஷெட்யூல் வந்து 9 o'clock தான் சார். இன்னும் பார்ட்டிசிபென்ட்ஸ் ஜாயின் பண்ணல சார். அதுதான் சார் வெயிட்டிங்.
ஓகே ஓகேங்க சார். ஓகே ஓகே, தேங்க்யூ.
நீங்க வீடியோ இல்லாம நம்ம வந்தாரு, நம்ம கேப்டன் வந்தாரு.
Dear participants, good morning to one and all. Hello. Is it audible?
Yes, sir. It's audible, sir. Morning.
Yes, sir. It's
Yeah,
audible, sir.
Yeah, good morning to one and all present here. So, Professor will join another 5 minutes. Please wait, right?
Okay, sir.
Okay. And one more changes in the session today. Afternoon, I think we are planning to give a lecture by one scholar from foreign university. Maybe he will discuss on tomorrow morning. So today afternoon, Professor Sasikala Madam presenting his lecture on today afternoon. These are changes on today. So I hope you are enjoying the lecture on today. Yes, your attendance will record it automatically. So because the Google Meet itself, we can download your attendance. No need to worry about your attendance. Maybe at the end of the session, we will upload in the EST portal. Don't worry about your attendance. But you have to maintain the attendance 80%. You know very well. As well as the test mark, you have to get obtain 60%.
Good morning, sir.
Good morning.
Sir, yesterday PPT you can have it somewhere because we want to go through it once again.
Your voice is not clear.
Sir, yesterday sessions PPT.
Yesterday's session PPT, so I will send it as soon as possible. Maybe I will send the recorded video. It is having with us. No need to worry.
How to assess that one? Because we just free our time, we will go through it so that it will be easy. Let us say, not find time to do it.
Okay, no problem. I will send it soon. So because the whatever the recorded videos, it will take 1 day.
Okay.
It is stored in the cloud. The
I
next
think,
day only we will collect the recorded video.
Okay, you'll be sending through what? Through link or something? Google OneDrive.
We don't know how to send. Maybe we'll discuss and then we will send it to you. Don't worry, or we will upload in the YouTube. No problem.
Okay, sir. Okay.
No need to worry about your PPTs. Some of the speakers are not send it as maybe they are taking in their own place.
Okay.
It is very difficult for to collect the PPT. Some of them they are sending, some of them they are hiding. That's why it is very difficult for us. Anyway, recorded video is possible.
But yesterday afternoon, we specifically want statistics that we want specifically.
Yeah, you are asking the professor, but we are also requesting to send PPT. He is telling that then some corrections is that then he has to give some more another 1 or 2 days.
Okay, so no problems. Okay, no problem. Okay, fine.
It is difficulty for the coordinator for collecting all the.
Okay, no, okay, I understand, sir. Thank you. No problem.
They are confidentially they are maintaining their PPTs.
But anyway, that is their own right. Nothing to do with it. But anyway, if they share it, please share it immediately, sir. No problem. Okay, thanks.
Okay. Sir is joined.
Yes, sir.
We will start. Good morning, sir.
Yeah, sir. Very good morning. My voice is audible to all?
Yes, sir.
Yes, sir. Audible, sir.
Manikandan.
Yes, sir. Yes, sir.
Who will Satish? Yeah. You can introduce, sir, and you can start the session. Thank you.
Good morning to all. So today's session will be. Yes. Good morning to all. First speaker,
Manikandan, your audio is not clear.
National Institute of Technology. Sir, 1 minute, sir.
Hmm. Mani?
Sir, 1 minute, sir. 1 minute, sir.
Hmm.
Morning to all. Let me introduce today's presenter. He is Mr. Nallathambi Shiva Shanmugham. He's joined in National Institute of Technology in Trichy as an assistant professor of mechanical engineering since 2008. He is currently holding the position of associate professor. He has received a BA degree in mechanical engineering from Bharatdasan University in 2002 and followed by ME in CAD-CAM from Anna University in 2004. He completed his doctoral research in finite element simulation pertaining to laser beam welding process in NITT in 2012. His research targets finite element simulation of welding processes, wire and arc, additive manufacturing, fatigue and biomechanics. He has authored more than 110 papers in international and national journals and conferences proceedings and has attended conferences in Slovakia, in Czech Republic, Austria, France, Singapore, and Thailand. Also, he is a reviewer of following journals: International Journal of Advanced Manufacturing Technology, Journal of Experimental Techniques, Journal of Materials and Design, Journal of Mechanical Engineering Science, Journal of Material Engineering and Performance. To his credit, he has completed several sponsored projects worth of 90 lakhs funded by B.H.E.L Trichy, NLC and DST. Currently, he is working in a sponsored project worth of 25 lakhs funded by ISRO Trivandrum. His teaching interests, on the other hand, include strength of material, finite element analysis, engineering graphics, welding technology, non-destructive evaluation, product design. With this short introduction, let me welcome Dr. Shiva Shanmugham, sir, for his lecture. I request to take over the session, sir.
Thank you, Sadish Kumar. And
Thank you, sir.
before entering into my today's presentation, I would like to place my sincere gratitude and thankfulness to the doctors, nurses, police, collectors, municipal staff, corporation workers, etc., who are continuously fighting hard against this coronavirus. And I also thank Dr. Raja Kumar and beloved Professor Dr. VB sir for providing me an opportunity to be a part of this wonderful faculty development program on simulation of welds and optimization techniques sponsored by B.H.E.L ACT. Thank you very much, sir. Thank you, Raja Kumar sir, for giving me an opportunity once again. And extremely sorry, friends, I thought of the program has been commenced at 10 o'clock. I forgot the thing. It is scheduled on 9:30 because most of the program started at around 10 o'clock. So it is penetrated into my mind. Extremely sorry for that. Anyway, I'll just compensate this 10 or 15 minutes during the break time, if time permits. If your coordinators are permitting me, then I will take extra 10 minutes after 11 o'clock. My voice is audible to all?
Yes, sir.
Okay. Sir, Rajakumar sir, நீங்க அந்த forumல இருப்பீங்களா இல்ல போயிருவீங்களா நடுவுல?
Sir, maybe I will present, sir. No problem.
Okay, no problem. Because I need some connection between the participants and myself.
Okay, sir. Okay, no problem.
Okay, thank you. Friends, and if you treat me as a friend, so I am normally I will treat everyone as a friend. If you treat me as a friend, my humble request to this forum is, please don't leave the meeting hall. If you have any urgent work, please don't move from that meeting hall. You just mute your mic and then move from here, because the practice, what we are following in our classroom or in some of seminars and all. So if you are continuously speaking from my side, if you are getting bored, then we are thinking that we are not in line with your with your presentations. I am coming out from the presentation thing. So please don't leave the meeting hall, because it is some sort of my morality will be changed. So if I'm thinking that if I want to give more information related to that finite element simulation, I am unable to do it, because the attitude will be changed. I think you can understand my position. My humble request, it is my humble request, please don't leave the meeting hall. If you have any urgent work, you just don't leave the hall. That is my humble request. So with this request, I'll just get into that. My assigned topic, today topic is assigned to me is on finite element simulation of welding processes. As I gone through your speakers, which is available in this B.H.E.L program, your organizer beautifully invited the speakers. So they are covering nook and corner of this simulation part, because the simulation is playing a predominant role in modern engineering sectors, not only on engineering sectors, in manufacturing sectors, in order to reduce the problem associated in the product development. Clear? So it plays a predominant role. That's why this program is specially coined beautifully in the heading of, under the heading of simulation of welds and optimization technique. So when you want to classify this research area, not only on publishing a paper in terms of the product development, we can categorize this research area under 3 broad classification. I think so. Most of you are aware of that anyway. It is my duty is to recollect, is to refresh your basics. That's all. See, when you go for this broad classifications, we have first part is of experimentation. Second part is something about, the first part is of experimentation. I'll just put it in the presentation mode. I think it is visible to all. First part is of that experimentation. Second is something about that analytical studies, and third one is something about C, and third one is of that numerical simulation. Correct? So whatever may be the problem, so it is not pertaining only to that welding, maybe you are metal cutting or something on the powder metallurgy, whatever may be the process. So you can put these 3. This is the broad classification of this research area. Correct? So when you put all these things under these 3 areas, see, based on the availability of the experiments, you can utilize the experimental facility and you can measure something. So please, my dear friends, I am using that appropriate word. If you are using the different words for different heading, your paper, your article or something about it will not speak in the international forum. Correct? When you go for this experimentation, I am carefully using that word measurement. So it is something about the truth. You are going to validate your truth once again. Correct? So you are depending on some sort of experimentation, some sort of machine tool to do the experimentation for measuring something. For example, if you go for this weldment, you are going to measure the weld bead geometry, or you are finding out you are measuring the residual stresses induced in that body. Correct? You are measuring the temperature which is available on the substrate material. Correct? That is of that experimentation. The second part, sir, it is very difficult for me. It is very, very difficult for me to get that experimentation facility. Then, sir, I am very strong in analytical techniques. So if you want to speak something to the IISc professor or very big IITs, then your guide or the expert who is available in the prestigious institutions they will ask surely about. So you have to put your question, you have to define your problem mathematically, correct? You have to write your equations and you have to define that problem, because they are very, very strong in that analytical techniques. Sir, I am very strong in analytical techniques. In side by, I am unable to get that experimentation. Then you can go for doing the calculations. It is not measurement, it is of calculation. You are calculating the temperature distribution, or you are calculating the height of the weld bead, as well as that something about the penetration depth or the bead width of the weld bead geometry. Correct? Sir, you are using some sort of equations and you are applying the boundary conditions to that problem, and you are applying the loading conditions to that problem, and you are analytically solving the problem, and you are calculating something on the temperature or something about the stresses. Clear? Sir, I am not good at analytical studies. I am very much interested to work something on these available codes, finite element codes, maybe of ANSYS, Abacus, Nastran, Patron, etc., etc. Sir, I am very good at. I am having very good idea how to simulate this problem. Then, what is the word you have to use it now? It is something about the prediction. See, if I want to go for this one, something on experimentation, you are using that word. I am using that word measurement or measure something. When you go for this analytical studies, what is the word you have to use it? You are going for calculation. I am calculate something, sir. I am calculation. And when you go for this numerical studies, you are going to predict something, correct? Sir, I want to predict the temperature distribution. I want to predict the weld bead geometry. I want to predict the stresses induced in the weldment, correct? Sir, if I'm using that word measuring using numerical simulation, it is absolutely wrong, my dear friends. That is a very, very important point I want to share with you. See, when you put whatever may be the problem, you can suit your problem. You can suit your problem according to this broad classification, experimentation, analytical studies, as well as on numerical predictions or the numerical simulation. Clear? See. Sir, when you are calculating something using analytical equations, sir, whether it is possible to validate the results? Yes, sir, you have to validate the results. Otherwise, your analytical data will not work, will not give the fruitful results. You have to validate the results. How to validate the results, sir? Sir, I can do some sort of preliminary experimental trials to understand the physical phenomenon of the problem. Then, with the help of the preliminary results, preliminary experimental trials, you can validate your analytical models that is used for calculating the stresses or calculating the temperature or calculating the displacement or calculating whatever may be the unknown parameter or the field variable. Clear? See, when you go for these analytical studies, you have to validate the results experimentally. Sir, experimentation is not available, sir. It is cumbersome, sir. You have to spend lakhs and lakhs of money for calculating something, for measuring something using experimentation methods. Then compare with the previous published literature and you can validate the results. That is the beauty of this analytical studies. Without validation, your research article will not be published at any time, at any cost. Sir, I am good at numerical simulation. Sir, whether it is possible to compare the results, analytical studies with the numerical simulation? Yes, somehow. Sir, it is something about, I don't know anything about that experimentation, it is of uncertain. Then in such cases, based on the problem, you can validate the results using numerical prediction. That is possible. Sir, what is the percentage of that error? So with the advent of science and technology, you see, the minimum percentage of error between the calculated results and the measurement. They are not publishing our article if you are projecting something more than 5 or 6%. They are asking us, you are finding out some sort of issues in the problem. So you have to reduce it. You have to go for convergence study or the stability analysis and reduce the percentage of error. Please, my dear friends, make use of this type of information in such a way that if you want to publish your article in a reported or you are working something on the product development, before going for the product development, you have to simulate the scenario and understand the basic phenomenon related to the problem. Clear? So in such cases, your percentage of error should be less than that of that 5%. It is very, very important thing. Please make a note of it. See, I think you are aware of that anyway. I am just refreshing the things. That's all. And sir, whether you can do it numerical simulation? Yes, sir, we can do that numerical simulation. But you have to go for some sort of approximation. Sir, I am not only going to discuss more on that welding because you are aware of that welding and this this faculty development program is coined not only giving more emphasis to that welding and what are the other techniques to simulate the conditions to understand the physics of that problem. Clear? Sir, numerical simulation. So it is something about that approximation, sir. So when you go for this finite element, these things are coming under the approximation technique, sir. Why it is an approximation technique? Sir, everywhere I am referring most of the books. I am referring the research article published in the open forum, even it may be a Sage publisher or it may be of ASME or elsewhere. So they are using some sort of assumptions. Sir, without assumption, it is cumbersome or it is cumbersome to simulate the scenario of the problem. It is not only the welding, maybe another manufacturing processes like incremental forming or powder metallurgy or whatever may be the problem. See, these all things are coming under that approximation technique. Even if you are adapting something about the finite difference method for finding out the heat flow, or something about the fluid flow, or something we are working on the build pool dynamics, then you have to depend on the fluid flow. In such cases, you have to depend on that constraint or something about another finite difference packages, or something about the finite volume packages. So these techniques are coming under the numerical approximation techniques. Sir, why, sir, these are all numerical approximation technique? And I am getting the exact solution, sir. Sir, it is very difficult to get that exact solution, sir. And when we are reviewing the most of the article, when we are seeing something about in the open forum, they are telling that, sir, it is very close, sir. I am getting very close. The experimentalization, the temperature distribution on a rod, I am getting the temperature distribution exactly what is available in the experimentalization. I am exactly matching with the numerical simulation. Oh, sir, because you are getting out a very high percentage of that error, but you are claiming that, still you are claiming that I am getting very close to the exact solution, and some of the researchers are claiming that, sir, this is the exact solution I am getting out based on the numerical simulation. How, sir? Because these things are coming under the approximation technique. You have to use some sort of assumption. If you are using some assumptions, you are neglecting something. You are not fully representing the problem what is available in this world. Correct? So if you are making some sort of assumptions, you will not get the exact solution of the problem. You will get only the approximating solution. That approximating solution should be very close to the exact solution of the problem. Sir, I am unable to get that point what you are emphasizing here. Correct? What I mean here, for that, I will give a beautiful example. Don't worry, friends, I am not taking more amount of time in giving something on finite element simulations, because I want to get the correlation between why I am selecting this finite element simulation for simulating my manufacturing process or my welding process. Clear? See, I am using that word, second word itself, I am using that, the truncation error. So that's why I'm coming out from the presentation mode, because there is some delay in that, especially in the Google Meet, because when you have a high DP pictures in that slide, if I'm moving the slide, you are not getting out that synchronization. Okay, anyway, I'll just come out from the presentation mode. Here you see, I am using that word, the truncation error. Sir, in the morning session, you are using that error term. No. It is not like that, friends. I want to impart that information, what I have learned, what I gathered the information from outside world. I want to disseminate that knowledge to this forum, friends. So what is the truncation error? Beautifully, please, my dear friends, relax yourself. It is a morning hour. You take a small, if you treat me as a friend, you take a small bit of paper. Even if you have a pencil in your hand, it's well and good. It is not described in any book at all. See, what is that, sir? Why you are using the truncation error here? See, for the example, I am taking one. I want to explain with an example. Without the case study, it is very difficult to explain any problem related to the mechanical engineering. I am taking an example here. Exponential of E of X. What is that? When you go for expanding this one in terms of the Taylor or the Maclaurin series, what I'm going to expand? 1 plus x squared divided by 2 factorial plus x cubed divided by 3 factorial. Up to that, what you can write, x power n divided by n factorial. Correct, sir? You can expand it throughout your lifetime. You can expand your series. Correct? Clear? And if I am assigning the value of x is equal to 0.5, if you want to find out the value of e power 0.5, you have the calculator and you are, sir, I am good at Excel, Excel sheet, I am good at MATLAB. Then if you substitute this value, that is, if you want to find out the value of e power 0.5, you are just to put that e power 0.5 here and you are getting out that value. I am not aware of that value. For example, if I am considering this as something on, if I am getting something on this case in such a way that, once again, okay. So I'll just take the different color. For example, the value what you are getting is something about 1.76527, like that. If you put it in the calculator, you get a very big value after the decimal point. Correct, sir? There is no round of value here. But here what I'm getting is something about, apart from the decimal, you are getting so many digits. So when you go for in-depth about the error calculations, especially in mathematics, sources of error, I'll just write here the sources of error in mathematics, it is divided into two headings. First one is something about the round of error. First one is something about the round of error. Second one is the truncation error, what I have indicated here, friends. Sir, first one is the round of error and second one is the truncation error. Round of error is aware of that. You know better than me, because what is that? The teacher taught you something in the mathematics. Sir, the value, after when you go for the decimal point, sir, I have the value something around 7.572. Sir, go for checking the third digit after the decimal point. If it is greater than 5, you have to give that increment value to the second digit. But if it is less than 5, whatever, you are going to neglect that part and will keep it as it is. 7.57. Sir, my value is something around 7.578. So automatically you are going to give the increment value to the second digit. Automatically, what is the value you are getting is something around 7.58. Sir, there is a vast difference between this one and this one. This is called that round of error. The error which is extracted by doing this round of the third digit, and you are putting the increment value to the second digit. There is a vast difference. There is a difference is something about 0.002. Correct? Sir, this is the error which are extracting by doing some sort of operation called round of error. Correct. Sir, what do you mean by the truncation error? Sir, the example what I have given here, what I want to emphasize here, what I want to mean here, if it is of e power 0.5, when you go for expanding this one, what is that? You can write throughout your lifetime. No, sir, I am not supposed to find enough time. So I want to truncate the mathematical procedure. I am going to neglect this part. I am going to consider only the first 3 points. That is a 1, 0.5, 0.5 square divided by the 2 factorial, and I want to find out the value of e power 0.5. I am not going to consider the 4th term, 5th term, 6th term. Sir, the error which is extracted, which is evolved by truncating the mathematical procedure is called truncation error. I repeat once again, my dear friends. Please don't think that it is irrelevant to this one. It is very, very important, my dear friends. Please, the error which is evolved, which is emerged by truncating the mathematical procedure is called truncation error. Sir, you are using the word approximation, but there is no approximation word is available in your definition. If we take the synonyms of the truncation, you can see that instead of truncation, you can use the word approximation. So now I want to change the definition in such a way that error which is emerged, which is evolved by approximating the mathematical procedure is called approximating error, because this finite element packages, this finite element methods, finite element analysis, finite difference method, finite volume method, boundary element method, these methods are coming under the numerical approximation technique. Why approximation technique? Because you are putting the barcode for the mathematical procedure. You are not going to wait until you are going for the infinite terms. You are converting the infinite terms to a finite value. See, you are changing that infinite value to that finite value. Automatically, the error which are extracted, which are emerged by doing this operation is called the truncation error. The other name for truncation is the approximating error. That's why I am claiming that, sir, when you are using this numerical simulation packages, numerical approximation method, you are getting only the approximate solution. But this approximating solution must be very close to the exact solution of that problem. How, sir? We'll go and see. What is that? I'll just take the case study and I'll explain you once again. See, sir, I am not convincing with your explanations. I want still more explanation. I want still more an example to explain it clearly. See, when I go for this type of a thing, see, what we have here, I am taking something about the differentiation part. As far as the differential calculus is concerned, how you can write that f dash of x is equal to limit delta x tends to 0, f of x plus delta x minus f of x divided by delta x. What is the physical meaning of this one? Sir, this delta x is something about very close to 0. Very close to 0, correct? Delta x tends to 0. Then this case is valid. But when you go for considering this numerical approximation technique, we are not considering delta x tends to 0. We are considering delta x as a finite number. What is a delta x? Sir, when you go for this grid, when you are going for discretization, the distance between the two nodes should be kept as minimum as possible, between of 0.1 or 0.01 or 0.001. Sir, it is based on the convergence. It is based on the stability criteria. I am assigning that size of that element, sir. Sir, what you are doing here, normally after the differential calculus is concerned, delta x tends to 0. But here, we are considering the delta x as a finite number. Then how we can write? It is approximately equal to, sir, if we want to exaggerate my part, f dash of x is approximately equal to this case. Why? Because I have considered this delta x as a finite number. Sir, previously I have considered one exponential and I have explained what do you mean by the truncation error. Now I have considered this differentiation. I have discussed to you why it is called finite element simulation, because infinite thing is converted to a finite by assigning a finite number to the differentiation. Correct, sir? Next, what is that I have? Next equation, I am talking something about more on this case and another integration. Sir, first one I have considered the differentiation. Now I am coming to the part of integration. What is the purpose of this integration? I want to find out the area below this curve. Correct, sir? What is that curve we have within the limit of a to b, f of x dx? Sir, I want to find out the area below this curve. What is that? Y is equal to f of x here. I am writing a function for y with respect to x. I repeat once again. I am writing a function for y with respect to x. What is the physical meaning of this? Sir, I want to find out the area below this curve. How to find out the area? Within the domain. What is the domain I have? Sir, a to b. A is the lower limit and b is the upper limit. Between this domain, I want to find out the area below this curve. Sir, what we can do, sir, because it is an irregular pattern, it is an irregular domain, how is it possible to find out the exact solution of the problem? No, sir. You are very difficult to find out the exact solution. Then, in English, there is a beautiful verb, beautiful proverb. Something is better than nothing. Sir, I am unable to find out the exact solution of that problem, but however, I can find out the approximate solution of that problem. But what is the method I am using? I am using the numerical approximation technique to find out the approximate solution of that problem, sir. Yes, sir. That is the thing I want from your side. For this case, I can pack known rectangle yields under this curve. Known rectangle. Normally, you have to pack infinite rectangle to find out the area below this curve. But I am not finding out enough time to pack infinite rectangle. I can pack only the finite rectangle of the known area. So that now I am packing, see, I have packed with the first rectangle, second rectangle, third rectangle, fourth rectangle. Even though it is crossing the curve, it is only an approximate area. If you add the 4 rectangle areas, then automatically you can find out the approximate area occupied by the curve within the set domain. Correct? But normally, exact solution is very difficult. But I can use this type of a numerical approximation technique to find out the approximating solution of the problem. See, that's why it is given here. Normally, you are in need of infinite rectangles to find out the area below this curve. Area below this curve, below the curve. But I am not finding out enough time. I'll just put only that finite number of rectangles to find out the area below this curve. Then the solution what you could obtain here by using this numerical approximation technique is only of approximating solution. You will not get the exact solution of that problem. Shall I give you one example? Sir, I am taking a cantilever beam. A load is applied on that beam. The deflection, what you are getting is something about y is equal to 100 mm is the deflection. That is the exact solution of the problem. Sir, I am using this numerical approximation tool. I will not get 100. Even I am getting only something around 99.98. There is a vast difference between that approximate solution and that exact solution, because 0.02 is that value. Sir, it is only the approximate solution, it is not the exact solution. But how close you are predicting the results based on the capability of the software, based on how you are approaching the problem. Clear, friends? Why I have taken out more than 10 or 15 minutes? I want to teach you, I want to enrich your knowledge that why it is called approximation technique. What is the solution you could obtain is only of the approximating solution. Clear, friends? So with this base, the purpose of giving out this preamble and all those things, if I'm creating a very good strong base, then we can make wonders, that we can create a bungalow, or we can create a mud house, we can create a kucha house, whatever may be the thing. If the fundamentals, if you are very strong in the fundamentals. See, coming to the part of the analysis part, sir, how to attack this problem?
Sir, audio is not
Sir,
audible, sir.
voice is not.
Siva sir. Hello. Sir, your audio is not clear.
So I think I moved my mic. Problem. Now it is clear?
Continue, sir. Okay. Oh, now it's okay.
I think somebody moved my mic. Thank you, friends, because the way of my presentation, I have opened in two systems. So if you want to speak anything, you can type it in your chat box. I can see your information in the chat box. Anyway, I thank Mahalingam sir, John, Vedesh, Viran, everyone. So if you have any doubt, you please type something in the chat box. It's my pleasure. It's my pleasure to answer your call. Okay. Now my screen is visible.
Yes.
Now my screen is visible to all. Yes, please.
Yes, sir.
Others,
Yes, sir.
please mute your mics. I am getting some sort of echo. Please. And I have opened another system. If you have any doubt, you please raise your queries. I'll answer your query. Okay. When you go for this physical process welding, so we have. I'll please make a note of it. You can categorize this one. Sir, kindly explain error graph. Sir, shall I explain it at the last, after lemon fine? Shall I explain, Sharanraj sir?
Yes, sir. Yes.
Yes, great. Thank you. I will explain it. Don't worry.
Sir, yes, I can discuss after 11:15.
Yes, please, sir. Please.
Sir, you can discuss during the discussion hour, sir.
You want?
Now you can continue your presentation.
No, I am not getting your voice. Please. You want to explain me now?
No, sir, you can continue.
Last session, sir.
Okay. Thank you. Physical process. When you go for this physical process, I am considering this welding. Sir, we can do this welding simulation under three headings. First one, you can consider as a heat transfer problem. HT. I'll just make it a short form. HT. Second one, you can go for the fluid flow. Second one is something about the fluid flow, and third one is something about a mass transfer problem. And if you have an idea, very good idea, you can couple it with phase transformation and also the stress distribution. That is something about complete representation of the physical problem. If you take the welding, you can do the simulation either in terms of heat transfer, second one in terms of the fluid flow analysis, and I am very strong in fluid mechanics, sir. I want to do something on fluid mechanics. Anyway, it's up to you. And third one is something about the mass transfer. And it may be decoupled with the phase transformation and the stresses. something about the residual stresses, or you can couple the heat transfer problem with the phase transformation, and simultaneously you can go for the structural analysis. Sir, I am very good at fluid mechanics. Then you can go for fluid flow. Then you can couple it with the phase transformation, or mass transfer. I can couple it with something about that phase transformation. It is up to you to decide what is the method I am going to adapt for simulating the problem. Here, I am going to consider only the heat transfer analysis in such a way that how depth I am going to consider this heat transfer analysis for simulating the welding process. Clear? Coming to the part of the structural analysis, why is a structural analysis? Because I want to find out the stresses induced in that body. For that, I want to couple the both thermal as well as the structural field to simulate the temperature distribution, and the temperature distribution has given us an input to that structural part for finding out the residual stresses and distortion evolved in the substrate material. Clear, sir? When you go for this structural analysis, is used to determine the displacement, stresses, strain, and forces in structure or components caused by loads that do not induce significant inertia and the damping effect. So when you go for simulating the structural analysis, you can consider different type of loads. The loads are discussed here, and you can find out that unknown field variable like displacement, stresses, strain, and the inertial forces, and the forces which is induced inside the structure, that also you can calculate when we are performing this structural analysis. When you go for the structural analysis, what are the loads that you can given as an input? First one, you apply the forces and also the pressure. Normally, when you go for theoretical side, it is very difficult to apply the force. There is no point load available practically. Correct, sir? So in that case, you have to apply only the pressure load. Pressure load means what? The load is occupied some area. Okay, it is something in terms of Newton per mm square or Newton per meter square. And when you go for this type of inertia, sir, I am throwing the ball. So it is something about the gravity. So you have to consider the gravity, that is G. It is something about 9.81. You have to consider for simulating your problem. Sir, I am going to use something about the bullet analysis. I am going to do some sort of penetration and perforation studies. In such cases, you have to work towards the gravity and away from the gravity. For that, you have to consider the G here for simulating the problem. And when you go for this non-zero displacement, that also possible to given as an input that is available in the structural analysis part. And third one, you can incorporate the temperature. As I discussed here, when you go for doing some sort of welding analysis, you are going to take the thermal, that is something about the thermal as an input to the structural mechanics problem to finding out the residual stresses. Residual stresses means what? It is something about the thermal stresses induced in the body. Okay. Sir, when you go for this thermal analysis, what are the things we can consider is capable of this available packages, or if you are writing your own code using your finite element in such cases, you have to understand whether the given condition should be varied with respect to the temperature or constant with respect to the, varied with respect to the time, or varied with respect to the time, or it is irrespective with respect to the time. You have to understand the loading conditions, then you have to given as an input to the model. Okay, so steady state thermal analysis calculate the effect of steady thermal loads on a system or a component. Sir, it may be working in hours, sir, there is no change at all. Then there is no need of taking the transient analysis. Sir, it is varying with respect to the time, sir. If it is of 5 seconds, it varies. It is different. When you go for 10 seconds, it is different. Example is something about you take a ice. You can take that ice and keep it in that room temperature. You can analyze in depth by performing this numerical simulation, because its condition is totally changed with respect to the time. And a beautiful example. When you go for the loads, what you are going to include for simulating your thermal analysis are convection. You can consider the radiation. It may be the heat flow. The same thing as I discussed in the structural part. What do you mean by the point load? Point load practically is impossible. Similarly, here the heat flow is also practically it's impossible. When you want to do something on simulation, you can consider the heat flow. You can apply the heat flow on the nodes. That is possible in thermal analysis. But practically, if you want to do something, there is no heat flow at all. Sir, when you go for the heat flux, you are going to apply with respect to that area. It is indicated in terms of that What is it? It is something about watt per meter square, or something about watt per mm square, or in some books they have used something in terms of the energy, joules, or in terms of that watts. Clear as a heat generation rate. You are talking something about watt per mm cube or watt per mm square. These are all something about with respect to the heat generation. And when you go for the constant temperature boundaries, that is another part. Sir, I want to raise the temperature. I am preheating that model. Sir, I am going to do some sort of preheating. I want to do something on stainless steel. I want to preheat it. Sir, how to define it? Sir, you can start the temperature from the preheat temperature, not with respect to the room temperature. Sir, it should be started from 200 degrees. Sir, I want to do something on additive manufacturing. Sir, I am keeping the dwell time of around 60 seconds. Sir, the temperature should reach only 200 degrees centigrade. Once it is reached the 200 degrees centigrade, I want to start the subsequent process. In such cases, the subsequent process should be started only with the room temperature, not with the room temperature. It should be started from the 200 degrees centigrade. That is possible by using the thermal analysis. Sir, why FEM, sir? What is the purpose of doing FEM here? Sir, the purpose of using this FEM, especially for this welding problem, I want to give the concrete reason, because whenever you are writing something about pen and colors are hiding the slides. Okay. That's why I put it in the presentation. Clear. See, when you are giving something about the research problem, you want to give a concrete base. Why I have selected this problem? Why I have selected this finite element method for simulating this thing? So you can go for analytical studies with that, because experimentation is available. Then why you are going for this finite element method? The answer for this question, beautifully narrated in this presentation, beautifully available in this slide, is the heat developed during welding process intermittently interact with the workpieces over a very short time intervals, resulting in very rapid heating and cooling cycles. As you are aware of that, when you are putting out the heat source, it may be a commercial arc welding process or a high energy radiant process or a solid state welding process. Whenever you are impinging the laser or whenever you are impinging the arc on the material, you are seeing. So when you are moving this arc, or when you are moving this electron beam, or when you are moving this laser with a very putting out that heat, you are getting out in terms of that solid metal is converted to a liquid metal. But at the adjacent side, you can see it is something in the solid state. It is something about in the solid condition. It is not in the liquid phase. So what happened? How we are getting out this weld peak geometry? So you are converting the solid metal to a liquid upon solidification, because upon solidification you are once again getting out something about the solid metal. So what happened? That is a phase transformation. Solid metal is converted to liquid, and if you are going for a high energy density process like laser and electron beam, you see you are getting out in the vaporization state. So liquid metal is converted to vapor. So some metal will be wasted from in the vapor form, and after removing of the heat input, after removal of the arc, after removal of the laser or electron beam, this liquid metal is converting back. It is converting to the solid form. So automatically we are getting out heating as well as the cooling cycles at the stretch. So the weld wheel is the product of a number of overlapping spots, and every point in the weld area experiences a complex series of thermal cycles during the passage of the welding heat sources. I am not pinpointing only with the laser electron beam or the MIG or TIG or CMT process. No. This complexity implies, sir, if you want to find out what is the temperature distribution at that point, it is very difficult to do it analytically, and it is very difficult to measure that instantaneous thing using experimentation. The only way is to do the numerical simulation and find out what is really happening. This complexity implies that analytical modeling techniques are almost impossible. Correct, sir? Almost, because you are going only with that. Even you can consider the transient, but this type of information it should be incorporated into the analytical part. It's highly difficult. I am not finding out. I am not telling that it's no way, but it's very difficult. So almost impossible. The finite element model, therefore, is the preferred option, although analysis requires a very large number of small time steps. So that's why I have discussed something about the infinite steps is converted into a finite. You are judging the length of the element because depends upon the welding speed, depends upon the heat source what you are going to consider. You are going for a discretization. When you are discretizing the model into a very small, a tiny, a very small element, and you are reducing the time. You are going for some sort of time steps. Then you can easily understand the physics of the problem. That is possible only with respect to the numerical simulation. Clear, sir? Now, I am considering laser beam welding as one of the case studies here. I want to, you will aware of that anyway. I just refresh your basics. You know something about laser beam welding is a keyhole welding process having a concentrated heat input. To obtain the required weld bead profile, the input process parameters have to be selected properly. Clear, sir? So you are aware of that. What do you mean by the keyhole welding? As soon as the laser impinging on the substrate material, the material under the beam partly vaporized, leaving behind the hole called keyhole is beautifully available in the schematic representation. If you take the first information, you see solid metal is available. You see the solid metal is available here. This is of solid. This is in the liquid form, and this is something in terms of that vapor. But when you go for this fluid flow analysis, you can consider this surface tension force, electromagnetic force, buoyancy force, etc., etc. But here, I am not going to consider all these things. I am not going to do something on fluid flow. I am going to consider only the heat transfer. How you have considered the phase transformation? By considering the enthalpy of the material. So, if we consider the enthalpy of the material, I am considering this. Indirectly, I am considering the phase transformation to find out the temperature distribution on the substrate material. Clear, sir? So when we go for the input process parameter, what are the input process parameter we have? Beam power, welding speed, beam angle, the spot diameter, exposure time. These are all the predominant input process parameters. We have so many input process parameters, but these are all the main predominant input process parameters which will directly affecting the output. What is the output we are going to find? We are going to find out the depth as well as the depth of penetration. So I have defined the problem clearly here. What is the purpose of numerical simulations? I have explained. Why I am going for finite element simulation? I have explained beautifully. Why it is called approximation technique? I have explained beautifully. Clear. Now I am going to consider this process. How I am going to consider the loads which is available in this process to the numerical simulation, to the numerical simulation packages, and what is the output I am going to generate. That are all things that I am going to discuss in the forthcoming slides. Clear? See, now we have, I think it is changed. The slide is changed now. Okay, now I'll put in the presentation. So those who are not aware of this laser beam welding, I am just going to play one beautiful video to exhibit that how the process has been taken care, how the process has been carried out in the industrial sectors, how we are taken out in the academic area. Clear? See, we have a beautiful thing, and you can see that molten profile. The gray color represents the solid, and the blue color represents your fluid, that is of in the liquid stage, and your rose color you can see it is in something in terms of the vaporization form. So it is something about a fraction of seconds. You are moving the laser with a very high speed, something around of 1 meter per minute or 2 meters per minute, according to the laser, according to the power, according to the material that you are going to fuse here. See, it is something in terms of that aluminum. So the melting point is something around in terms of 600 to 700 degrees centigrade. If you convert in terms of Kelvin, it is very close to the 1000 degrees centigrade. So it is crossing that solid to liquid metal. Once it is further heated to once the material is further heated, it is reaching the evaporation state. That is also available here. It is given in the chart beautifully. What is the temperature related to different zones, that is highlighted clearly. This is only a schematic representation. That's why you are finding out more insight about the process. Okay, and the keyhole you can see in your eye. See, as I discussed, once the laser impinging on the substrate material, the material under the beam partly vaporized because it reaches the vaporization state something around 2500 to 3000 Kelvin. So there is no metal at all. but it is like it is like putting a pencil into a cheese. When you are putting a pencil into a cheese, automatically the pencil will be penetrated into the body. Correct, sir? But the portion covered by the pencil will be free from cheese. Correct? The portion covered by the pencil will be free from cheese. But when you are removing the pencil, the nearby melted metal or nearby cheese which is available is getting into the keyhole and it will fill the keyhole. Correct? So it is very difficult to see the keyhole in the naked eye. But you can see only the pinhole after completion of the process. When you examine the welded metal, when you examine the welded sheet metal, you can see a small pinhole which is located at the end of the pass. Correct? So that is how I want to explain, because these are all the scenario you have to explain it, you have to simulate it. Then only your problem, selected problem, will be provide the fruitful results. Otherwise, will not provide the fruitful results, and your article and your process will not be published, or your paper will not be published in your open forum. Correct? Why I am discussing each and everything here, you can easily simulate all those things, like a keyhole separately, you can find out the vaporization hole separately, you can find out what is a weld bead geometry separately by simulating the problem. Clear? Now, coming to the part, we have why to do modeling, sir. What is the purpose? Sir, you have beautifully explained it, your explanation is available. See friends, maintaining the laser beam welding process in academic institution is highly difficult, because it is like an elephant. You have to feed the elephant continuously, and making out that process, you have to keep the chiller unit. So you have to maintain the equipment in and around. You have to spend more amount of that money. Sir, and creating a joint, and if there is a problem with the fiber optic cable, because I am using something about 1.06 micrometer wavelength, it is something about a solid state laser, NDOC laser. And if it is of a carbon dioxide laser, it is a high power laser. Maintenance is very, very difficult. And if you want to do some sort of joints, you have to go for the joint configurations. You have to, it is something about the zero air gap between the square butt. So these are all the problem associated with it. So what we can do, we can do only the preliminary experimental trials. With the knowledge of the preliminary experimental trials, you can do a simulation, and you can validate the numerical simulated results with respect to the experimentation with the preliminary experimental trials. If you want to correlate with all the input parameters and output, then you have to make 1,000 joints at a time, and you have to do that analysis. It is very difficult, and you have to spend more amount of time as well as the money to understand the effect of input process, complete effect of the input process parameter on the output. But for that, we are very difficult to find out the time, and also very, very difficult to spend money. Correct? Then you can do a modeling, apply the load, and solve the problem, and find out the scenario behind that. So once the optimized parameter have been selected, then you can use the optimized parameter for validating the results, and you can go for the product development. Even it may be of titanium, or it may be of inconel, or it may be of a stellene, whatever may be the material that you are going to consider here. You can change only the material property, you can change only the boundary conditions, you can change only the heat input. Automatically, you can simulate any number of problem at a time. Within a single room, within a day, you can find out the correlation between input and the output. Sir, why to do modeling, sir? Phenomena. Sir, here I have considered a laser beam welding. I am going to simulate this phenomena numerically. Geometrical modeling and simulation via computers have reached a level to replace the real life. Correct, sir? This is the point I want to emphasize here, my dear friends. Real-time prototypes or the trial runs. There is no need of conducting the trial and error experimental trials. Directly, you can understand the process. You can make number of simulations. Out of the simulations carried out, you can find out the predominant factor. What that factor, you can directly feed that input to that experimentation, then find out the results. A geometric model is defined as a complete representation of an object that includes both its graphical and non-graphical information. Maybe you can put it in the graph form, or you can get that something about the pinhole that I have discussed here. The pinhole analysis is non-graphical form. It is not like that, sir, when I am increasing the beam power, automatically the depth of penetration has been increased, the beam width has been increased. No, it is in terms of the graphical, direct correlation. I am indirectly correlated. What is that? Sir, I can simulate that what is the tail end, what is the length of the tail. If we increase the welding speed, what is the length of the tail? That and all is something in terms of the non-graphical form that we can do it only with the numerical simulation. Okay. So coming to the part of that actual experiments versus modeling, compared with experimental methods, the computer simulation based on various numerical methods. As I am not only pinpointing that finite element method, friends, I am also working towards on finite difference method, finite volume method, etc., boundary element method, etc. Even extended finite element method. This is a meshless thing. So it is not depending on mesh. It is irrespective of the mesh. You can simulate the problem. Various numerical methods is becoming more and more popular in the investigation of the process because of the reduced cost, increased speed of the computation, and the capability for analyzing the effects of different factors. This is a very, very important point I want to emphasize. Sir, I want to get all the input process parameters. What is the direct effect of all the input process parameter on the output is the only thing where you can do numerically. Involved in the process separately. Each process parameter, what is the effect, what is the effect, everything you can do it solely here with the help of this process. So finite element is a computer-aided mathematical technique because doing it in the paper nowadays is very difficult. I can add some more point here with respect to this definition. Computer-aided mathematical technique for obtaining approximate numerical solution to the abstract differential equation that predicts the response of the physical system subjected to external influences, the boundary conditions. You are going to give the loading conditions, you are going to apply the boundary conditions to that problem, then you are simulating the problem numerically and find out that approximate numerical solution. So a powerful program helps in manipulating the matrices for solving simultaneous equation is used for this purpose. Sir, when I am considering this abacus, there is a separate module called abacus welding interface. You please make a note of it, friends. When we are using that abacus as a tool, as a finite element code for simulating the problem, we have a separate module called AWI. That is of abacus welding interface, and you can use your Fortran subroutine. We have a Fortran, so Fortran subroutine for creating your own heat source model, and you can repeat the heat source model for numerical simulating the problem. And sir, I am not working on abacus. I am very strong on ANSYS. Then we have a separate module called APDL, especially in ANSYS. That is called the ANSYS parametric design language. Now they have introduced one more small patch in your ANSYS called ACT. That is of ANSYS customization toolkit. In that you can directly simulate that problem, especially welding, incremental forming, metal cutting, and all. You can use this ANSYS customization toolkit. It is incorporated in the ANSYS workbench for simulating the problem. Okay, so these are all some of the general steps adapted for simulating the problem. When you go for the experimentation, as I discussed with the phenomena, as I showcased that one beautiful schematic representation how the laser beam welding has been carried out in the industry. So this is that I want to thank Welding Research Institute, and I also thank my guide Dr.G.Vimalan, a very big man. I want to thank in this juncture. I want to thank him for providing the experimentation facility. It is a 2 kilowatt ND laser, and it is divided into 4 compartments. Each compartment is capable of producing that 500 watts. It is connected in the series. The total output what you are getting is something about the total power output what I am getting is something about 2 kilowatt. It is a solid state laser, and you see the laser head. All the parts are available here. You can get more information this one, and it is a 1.06 micrometer wavelength, so you can easily transport this laser through fiber optic cable. But when you go for the 10.6, you are not supposed to do it with the fiber optic cable. It is something in terms of pipes you have to transport it. It is something about the carbon dioxide laser, gas lasers, and you are aware of them, this laser radiation is affecting your eye. So the entire process has been closed and it is closely monitored, and everything it is an automated one. And you can see the purpose why I have why I have incorporated this picture here. Especially this laser head is not kept straight. It is not kept straight. Here, see, it is tilted in such a way that it is maintaining some angle with respect to the substrate, with respect to that vertical. You see, if I'm drawing this line, if I'm supposed to draw a line here, so this line is something about a straight. It is something perpendicular to the substrate. This laser head is kept in some angle. So laser beam angle, we are maintaining some laser beam angle. The purpose of this one is whenever the laser, because we are playing with the light energy, you know that laser is light amplification by simulated emission of radiation. Whenever the laser is impinging on the material, it is reflected from the substrate. Especially when you go for this aluminum and all, you are getting a very high reflection. Because of this reflection, what will happen? This reflected light will hit the laser head and it will create damage to the laser optics. Correct, sir? Sir, the laser optics it's very, very costly. So something around 12,000 rupees. The optics which is available at the end, it is only the protection lens. It is only the protection lens what is available at the laser head. Because of this back reflection, when you are keeping the laser head in a straight, in a perpendicular position, because of this back reflection, it will damage the optics. To avoid that, this beam angle is kept with respect to that vertical, maybe something around 5 degree with respect to that 5 degree with respect to that vertical, or it may be 85 degree with respect to that horizontal, whatever may be the thing. You can keep the orientation with respect to that substrate or with respect to that vertical. The purpose of this keeping the angle in such a way that, so you have to concentrate the energy on the substrate, and to avoid the back reflections, we are keeping the setup in such a way that with respect to that vertical, we are maintaining some angle. Okay, and as I discussed with you, see, and coming to this part, when you are going for this laser beam, so you know we are playing only with the light energy. I don't know how the energy is distributed across the beam. See, it will be converged to a particular point. Sir, if it is of the laser head, and this is something about the substrate, you are going to concentrate the beam to a particular point. Okay, where you are going to do the joint or where you are going to do the bead-on trials, you have to pinpoint that laser to that particular position. Correct, sir? You are focusing the laser to that particular position. So what is this? This distance is called that focal length. FL. This is called the focal length. So it depends upon the focal length, you are getting the spot diameter on the substrate. Correct? And my anticipation is whatever may be the energy that I am keeping here. For example, I am operating that power, input something around 600 watts beam power. Whether this 600 watts is uniformly distributed along the cross section, across the section, whether it is distributed. For that, we have procured one laser beam analyzer, which is having the capability to find out how the energy is distributed across the beam. So that is the part I have incorporated here. I want to thank the DST for funding this project. I am not pinpointing on the substrate. I am pinpointing on the GG17 glass. It is called the arsenic glass. It is having the capability to absorb the laser. It will not reflect that energy, it will absorb the laser. So it is used for tuning the laser in such a way that whether the energy is distributed across the beam uniformly. Correct, sir? So that is one of the beam that we have captured during our experimentation trials. You see, it is like a Gaussian beam. Correct, sir? It is like a Gaussian beam. So why you are giving more emphasis? You can raise this question, sir. Whenever I am giving a heat input to that model, I want to teach the answers or abacus that how the energy is distributed, whether in the form of Gaussian or only the energy is peaking at the periphery, not at the center. You see, in the previous case, I'll just put it in the presentation mode. You can see something about it is not uniformly distributed. The energy is getting only at the periphery, not at the center. But the help of this laser beam analyzer, we can adjust the lenses in such a way the energy should be uniformly distributed and the energy should be peaked. It should be peaked at the center of the beam. That is the beauty of doing this type of analysis in such a way that to find out how the energy is distributed, what is the method, what is the profile of the energy distribution, which is highly helpful to given as an input to that model. Okay, sir. The material considered for that experimentation is only of AISI 304 stainless steel. It is an austenitic grade. We are also calling this material as an 18% chromium and 8% nickel material. The melting point of this material is something around 1400 to 1455. So each and everything available in the slide will have a coherence between the previous slide and the next slide. I will tell. So why you have indicated this melting point? Because of this melting isotherm. With the help of this melting isotherm only, I want to predict the weld bead geometry that I will discuss in the forthcoming slides. Sir, how you are going to simulate the problem? Sir, I want to create this three-dimensional model. What are all the inputs? What are all the inputs that I am going to provide here? Sir, whenever there is an impinging, you can see the heat is going to propagate on the top surface and this heat is going to penetrate into the material. See, when I want to simulate this scenario, I want to find how the heat is distributed. So when you go for the top surface, you can see it is like a surface temperature. It is only of a 2D. But when it is getting into the material, it is converting from 2D to the 3D because heat is dissipated along the all direction. It may be in the X direction, Y direction, and Z direction. Then how to select the heat source models? There are so many heat source models are available. If you want to get more exposures with the heat source model, I think your coordinator Rajakumar sir is also arranged some professors who are giving more input to the heat source model. But if you want to get more heat source model, you can go to the lectures of Professor Panikumar of IIT Madras. He is providing so many information related to the heat source model. Anyhow, I am going to give you something about the gist. How to select the heat source model for simulating the problem. Here, it is converted into a surface heat source equation, and the second one is something about the volumetric. This is only on the top. It is along the thickness direction. Correct, sir? It is along the thickness direction. Okay. Sir, for this one, what are all the input for the surface heat equation for the volume? Sir, I am using the laser power as an input. What is the input in terms of the watts? And how much time I am going to expose the laser, the time. And what is the beam angle I am going to adapt for impinging the laser, and what is the spot diameter of the beam, whether it is of a 0.8 mm or 1 mm or 1.2 mm. This has been taken out from that laser beam analyzer, because you know that when you are using this focal length, what is the spot diameter of the beam, how the energy is distributed. So, and volumetric heat source, I am getting more input from the keyhole radius. It is very difficult to measure the keyhole radius, but analytical modelings are available. It is available in the open literature. Based on the selected material, based on the selected process, I have taken out the information about the keyhole radius. It is something about a 0.3 or 0.4. So predominantly they are using only of the 0.3, going with respect to that 1000 watts or 1200 or 1500 watts. It is taken out from the literature. And we are going to give all these informations to the finite element model. In addition to that, I am going to teach about the thermal input boundary conditions. What about when you are introducing the laser, it should be in the room temperature. When the laser is going to touch, it should be in the room temperature. You are going to introduce the laser along the y-axis or z-axis or x-axis. Depends upon the model that you have considered. You have to assign the initial as well as the boundary conditions to that model. And I am going to consider this process as a temperature dependent, something about the material non-linearity. When you go for this finite element simulation, we have three different non-linearity. First one is the material non-linearity, second one is the geometrical non-linearity, third one is the contact non-linearity. Please make a note of it. I am not finding out enough time to give more information on the contact non-linearity and geometrical non-linearity. But here I am going to give only that temperature dependent properties. You see, the thermal conductivity of the material will be varied with respect to the temperature, and your Young's models will be varied. When you are conducting the tensile test with the room temperature, you are getting out that Young's modulus in a different value. So when you are going for an elevated conditions, you are getting a different Young's modulus value. So these are all the information that they have to feed to the system in such a way that you have to teach the answers or abacus that this is the material model I am going to consider for performing the numerical simulation of laser welding processes. Okay, after giving all the input, I am going to solve the going to extract the temperature distribution. After getting the temperature distribution based on the melting isotherm, as I indicated in the previous slide, what is the temperature, what is the melting temperature of the set material? It is only of 1450 degrees centigrade. And with the help of this melting isotherm, I can predict the well-being geometry. What is the fundamental behind that? The material, the area which is encompassed by the isotherm more than that of 1450, it is relevant to the well-being geometry. Clear, sir? That I am going to discuss in the next slide. So the blue colors are indicating the input given to that model, and the red color or the red color, that is a pink color, indicating that output what you are extracting from this model. See, now coming to the part of how the program has been developed here. How the program has been developed. See, it is something about I am going to perform only the transient thermal analysis. I am not going on as steady state because it is depending on the time. When the welding speed is of 600 mm per minute, you are getting a different temperature of the constant beam power as well as the beam incident angle, etc., etc. And when you are enhancing the welding speed, you are getting out that minimum temperature because your interaction rate is very, very high. Okay, well, sir, starting transient thermal analysis, you are going to create the finite element model. Then you are going to give that all the temperature dependent material properties, conductivity, density, enthalpy, specific heat, and I'm going to give the boundary conditions, convection and radiation heat transfer. I'm going to consider for performing the simulation, and I'm going to apply the heat flux to the corresponding nodes. Depends upon the spot diameter of the beam, obtaining the Dixon coordinate with respect to the nodes, calculating the heat input based on the heat source equations, applying the heat input on the respective elements. Each you have considered as a separate load step and deleting the previous load step, and I'm going to run the entire load step from 1 to 100 or 1 to 200. And if all the elements, if the heat is applied to all the elements, then the process is going in a continuous manner. If it is yes, then you can go for solving the system. From that, you are finding out the temperature distribution and obtaining the well-being geometry. So this entire thing, this entire thing is called the pre-processor. This phase is called the solution phase. And the reviewing the results, you are doing the post-processing the results. I'm going to find out the temperature distribution. I'm going to find out the stresses induced in the substrate material. So these are all called the post-processing. Okay. So next one, we have the governing equations. It is something about the Fourier heat conduction equations. We have a rho Cp, that is something about the enthalpy of the material, what I have considered here for the phase transformation, and the velocity you are giving in terms of the y direction. You see, it is given in terms of the y directions. You are considering the thermal conductivity on the x, y, and the z, and QV is something about the volumetric heat source I am going to give as a heat input to the model. Okay. Sir, as I discussed with you, there are so many heat source models. I have given only a very few here. See, we have a Golden heat source model. We have a simply Gaussian heat source model. We have a conical Gaussian. Even modified conical Gaussian is available. And my scholar Dinagaran developed his own heat source model, that is of a parabolic Gaussian heat source model. So many heat source models are available. Sir, how to select the heat source model? See, when you go for simulating only the conventional arc welding process, this is based on that experience. If you are really interested to work in this area, I can give more information to me. I will feed more information to you, friends. I already given my email ID as well as the mobile number. Anytime you can trouble me and you can get more exposure in this area. Sir, I will give only a small information related to the heat source modeling. When you go for simulating that plasma arc welding, TIG welding, MIG welding, cold metal transfer, you can utilize your Goldak double ellipsoidal heat source model for simulating the conventional arc welding process. Even plasma also you can use this process. You can use the heat source model for simulating the plasma. Sir, I want to go for only the heat treatment. Sir, I want to go for only hardening the metal. It is like you can use your high power laser for making out to change only the grains available on the periphery of the material. I want to hot phase it. I want to clad it. There is no need of finding out the temperature distribution along the thickness direction. Then in such cases, I am only working on the surface treatment, surface modification technique in such cases using arc welding. Using arc welding, even you can go for the high energy gradient process like electron beam and laser. It should be operated in a low power mode, not on the high power mode. Okay, sir. Otherwise, you can defocus the laser and you can scan the laser on the low power mode to modify the surface of the material. In such cases, you can use the Gaussian. Sir, I want to find out the temperature distribution along the thickness as well as on the surface of the material. I am using the laser as well as the electron beam. In such cases, you can use your three-dimensional conical Gaussian. So I am using the plasma arc welding for performing the keyhole welding process, because you know that keyhole welding process is categorized into three different things. We have a laser, we have an electron beam and plasma. If you operate the plasma with a very high power, then you can operate in a mode of keyhole mode. Similarly, when you go for this laser in a high power, maybe something around 2 kilowatt or something about more than 2 kilowatt with the low welding speed, you can achieve this keyhole mode of welding. Similarly, when you go for the electron beam with the high power, you can achieve aspect ratio is very high, sir. So I'm getting a depth to width ratio more than 1. Depth to width ratio, penetration depth is higher than that of the B.H.E.L. In such cases, you can go for utilizing this 3D conical Gaussian or a parabolic Gaussian model. It is also called the Vimalan's model. My scholar introduced my model, developed his own model for simulating the plasma arc welding of titanium sheet. Simulating the plasma welding. So, based on the profile of weld bead geometry, next slide. Sir, based on the profile of the weld bead geometry, how to select the heat source model. Sir, my intention is I want to work on hybrid, laser hybrid welding. I want to simulate the process. In such cases, you can go for how the heat gain, how heat is given as an input to the model by the combination of the heat source model. Like you put the golden heat source model on the top and the conical heat source model at the bottom along the thickness direction. You can combine the heat source model and you can simulate the process. This and all, how you are giving that information, sir. Please tell me how you are providing the information to us. Sir, it is based on the profile of weld bead geometry. Based on the profile of weld bead geometry, you can simulate the problem. Clear, sir? So this is the schematic representation of the conical Gaussian. You see, as we discussed in that laser beam analyzer, the profile, the heat is distributed, the energy is distributed in the Gaussian profile. So that's why it is in the form of Gaussian, and along the thickness direction, it is in the form of conical frustra. Sir, how you are considered based on the profile of the weld bead geometry. Next slide, I will show. And these are all the equations related to that conical Gaussian heat source model. It is divided into two parts: surface heat source as well as the volumetric heat source. See, in the surface heat source, we are talking only with respect to X and Y. And when you go for that volume, you are going for the Z direction. How the heat is distributed along the thickness of that material. Okay, sir? How the temperature is distribution on the top, how the heat is distributed on the top surface along the thickness direction. You see, all the equations are provided here. Sir, H is indicating the height or the thickness of that material, and it is like an elephant's trunk because it is something about based on the number of experimental trials they are finding out this is the geometry of the keyhole. Why is that? As soon as the laser impinging, if you are operating with a 1 kilowatt power, you see, this is we have a 1 kilowatt power, but when it is digging into the material, it will lose it. It will lose the capacity. Heat will be dissipated, and when you go for that depth, it will not operate only with the 600 watts because energy is distributed along the all direction. So only minimum heat is available at the tip at the. So it is not like a straight one. What is available? What I have made in the previous thing, it is only for a theoretical thing. But normally, when you go for a practical exposure, you will not get the straight like a conical. It is like a bent. As if you recollect, if you have shown the video that I have showcased in the laser beam welding process, you can recollect this one. The keyhole which is available in that video is not straight. It is like a elephant's trunk. It is bent towards the movement of the laser. Because it will lose the capacity, the heat is distributed along all the directions. And based on the preliminary experimental trials and all the literatures that we have dealt, see, only 25% of the energy is accommodated. Something around only the 25% is accommodated at the top.
and remaining 75% only will be penetrated into the material. It may be changed, depends upon the materials. For example, here in stainless steel, 25% of the output, that if it is 600 watt, out of 600 watt, only 25% will be distributed at the top, and the remaining 75% only will be penetrated into the material. If it is for the aluminum, the cases will be different, because aluminum is having a very high reflectivity. The absorbability of the material is be very, very minimum in case of aluminum material. Correct, sir? So now, after understanding the physical phenomena, after understanding the equations pertaining to the heat source model, you can give the input to that model with different joint configurations. Once you could understand the problem, then you can create this one in terms of joint configurations, or a T joint or a lab joint. You can place one over the other, and you can do the simulation. This is how we are calculating, this is how we are performing the simulation on different joint configuration using the conical Gaussian heat source model. And coming to the boundary conditions, what we have the initial boundary conditions and the essential boundary condition at y is equal to 0, because you are going to put the laser along the y-axis. The entry is along the y-axis, along the direction of the y-axis. So at y is equal to 0, it should be in the room temperature. If the maintained room temperature is of 20 degrees centigrade or 25 degrees centigrade, it should be in the room temperature. And before the commencement, T is equal to 0, it should be in the room temperature. And these are all the things which is pertaining to that, how the convection along the surfaces, top surface, side, and also the bottom, that you are keeping on the weld, on the table, work table, that is also subjected to a convection as well as the radiation heat losses. These are all the things that I have considered as a boundary conditions to simulate the problem. Okay, and coming to the boundary conditions, we are considering both three. That's something about the convection, conduction, radiation, for exactly simulating the environment conditions available in the laboratory. Okay, and coming to this part, see, as I discussed with respect to the beam incident angle, so I said I am not keeping the beam straight. If I am keeping the beam straight, I can get exact circular profile on the substrate. But when I tilt the beam with respect to the vertical, I am not getting the circle, I am getting only the elliptical shape, because the heat is not, because your profile is not almost a circle, it may be in the form of elliptical shape. So once it's elliptical shape, the energy is not fully concentrated on the circle, it is fully dissipated in the elliptical form. That is how it is created here. It is schematically presented here, circle, elliptical profile, and this how we can do the simulation. After creating that mesh, after finding out the refinement of the mesh, so what is the refinement? Wherever you are putting out the more focus, that area should be fine mesh, should be refined properly, and wherever your unknown parameter is relatively constant, you can go for the coarse mesh. Okay, sir. And these are all the assumptions that I have made here. These are all the assumptions. I am performing only the heat transfer, the temperature dependent property are considered, latent heat of fusion is considered for taking the enthalpy of the material to consider the phase transformation. Conduction and radiation loads are considered as a lumped heat transfer coefficient, and the buoyancy force, viscous force, convective melt flow, Marangoni effects are neglected, and go for aluminum, it is very minimum. When you go for something about with the stainless steel, it is only of 69.3%. It is something about the efficiency of the process. Clear? So after making this one, we are creating a different parts, different spots on the material with that. Before going for a laser seam welding or a continuous laser beam welding, so I am going to create a different spots to understand the physical phenomenon behind that. After simulating this one, I can have a better understanding of the process. I can move the laser beam with the required welding speed. Clear, sir? These are all the process parameters I have considered. I am considering the full factorial design. 3 power 27 trials have been created. See, and all the profiles are being investigated using the optical OM. that is something of optical microscope. You can get that the different profiles. You see, it is not almost circular because everyone, it is something about an elliptical form. You can see it is in the of elliptical form. It is not circle because I am not keeping the beam straight. I am keeping the beam in an inclined position. The energy is not created on that surface, is not uniform. It is something about in terms of elliptical shape. So this, why you are giving more emphasis? This you can validate. This you can cross check with the numerical simulation. If I want to validate my numerical simulation, this phenomena should be there in the numerical simulation. This is for different beam power, beam exposure time, and beam incident angle. And this is the spot which have been created. So this is the beauty of the simulation. So what is that in the Tamil? We are using that. It is an exact replica of all the simulation that I'm going to perform here. See, you can create a twin spot with a different exposure time, and you can find out how the temperature is distributed. See, first spot is created with one predefined exposure time, and the laser head will be moved to the next location. It will create a next spot. So you can understand one spot is in the cool stage, another part in the heating state. That you can easily find out. As I discussed, what is the purpose of FEM? The justification of the FEM is validated here. It's been proved here. See, this is how you can get that simulation. See how beautifully you can get that simulation. One spot is in the cooling stage, another spot is in the heating stage. You can find out what is the intermediate time to get the negotiation between the first spot and the next spot. So from that you can easily understand how the spots are created, what is the distance between the two spots should be kept, everything that you can easily understand by making a number of simulations here. So I'm going to play another beautiful video here. Beautiful video. So first spot has been created with the predefined time, and the laser gate is moved to the next location, and it is going to create the next spot. Sir, I want to find out what is it in the cooling state, what is the temperature related to the cooling state. In the solidification state, what will be the temperature? In the heating stage, what will be the temperature? From that, you can easily understand the temperature distribution and the spot diameter, and also the weld bead diameter of the weld bead geometry of the material. You see, so after this one, I have captured the temperature distribution. I captured only the profile of the weld bead geometry. In order to validate my code, develop APDL, sir, I can use a different heat source model in the code, and I want to validate that whether the written code provides the purpose or not. See, in the first case, I have used only the Gaussian. In the second two models, I have used the Gaussian heat source model. So a three-dimensional conical Gaussian heat source model. You see, both the cases in the Gaussian, as I discussed with you, it is giving only the temperature distribution at the top. And in the thickness direction, there is no such cases are available. Okay, but when you go for the conical Gaussian, you can see the beauty of the thing. You can get the temperature distribution at the top and also along the thickness direction. So the capability of the developed code will be utilized for whatever may be the heat source model that you can use it. You can incorporate the heat source model and you can simulate the problem. It's not only for laser beam welding, it is used for laser scan, that is of laser surface treatment process, or you can use your arc energy for the surface modification technique. And you can incorporate, you can extract all the data to the MATLAB and find out what is the temperature gradient related to this one, and you can capture, you can validate the results. As I discussed with you friends, purposely I have damaged the lens to understand whether I am getting an exact circle when I am keeping the laser head at a straight, at a perpendicular to the substrate. I can create, you can see a beautiful circle. A spot has been created in a circular form. It is almost a circle, and you can see it is almost in a conical form. So based on this assumption, based on the profile geometry, I have selected three-dimensional conical Gaussian is the better heat source model for simulating the laser beam welding. Like that, you can do some preliminary experimental trials, section the sample, do the microscopic, do the metallurgical studies, take the macrograph of the weld metal, and from that you can take the available heat sources and do the simulation. And this is how we are validating the results, and it is almost very close, but I am doing lot of assumptions. I am not getting the exact match between the approximate solution and the experimentation. Validation is very important, friends. Okay, sir. After that, you can change your process parameter. You can change your welding speed, or you can change your beam incident and not welding speed here. It is a spot. It is a spot welding. So changing beam incident, beam power, changing the beam exposure time, and you can compare the results with the experimentation and the numerical simulated results, and you can find out the profile. As I indicated you, as I discussed with you, is something about the elliptical shape. It is evident from these projected results. Along the depth of the penetration, when the wide beam is wider, you are not supposed to dig the material. You are getting only the partial penetration. It will not fully penetrate the material. So because of that wider beam angle, you are getting out only the lower depth of penetration. That is available here. So, and also we have used the console for simulating that problem. It is now I have changed the from stainless steel to the glass. As I discussed with you, the GG17 glass. It is of arsenic glass, which is having the very high quality of absorbing the laser through. It will absorb the most amount of the energy from the laser. So it has been utilized using the console. The beauty of the console is you can write your own equations. You can teach the answers. You can teach your models, not answers. You can teach the entire model with your own equations. That is the beauty of the console. If you want to get more exposure, please contact me. I will enrich your ideas in this console. So this is the equation which is used for simulating the Gaussian heat source model on the material. So these are all the assumptions we have used, and this is the mesh we have adapted for simulating the problem. And this is one of the simulation that we have performed. See how the temperature is distribution on the glass material. See, the temperature distribution is very minimum. It is starting from 300 Kelvin to something about 332, because it is a glass material. Even minimum amount of energy is sufficient to fuse the glass material. Okay, like that. Once you are coiling out a very good strong base on spot welding, so you can move the laser, because I already proven myself, I already proven my technology, my code performing good in all aspects, then I can move the laser with different speed. And this is one of the trials we have performed at the welding university. You can see it is invisible to eye. It is only that that is a heat that is coming out from that. It is evolved from the material. It is on that SS. After that, these are all the bid-on-plate trials to understand the process parameter. So the mode, what I have adapted is something about the transverse, the electromagnetic mode, 1000 mode. This mode is used for doing the welding. We have a different modes, 01, 02, 011, 022 for surface modifications or going for drilling. You can use the same laser for using the drilling operations or cutting operation. You can operate with the different modes. So once you understand the concept, once you understand the phenomena of the material, phenomena of the process, understanding the numerical simulation, you can move the laser with a different speed. As I discussed with you, I have divided into number of load steps. Totally 200 load steps I have considered for both the heating as well as the cooling. You can see, you can easily understand the pin as I showcased with in the schematic representation of that video. The pin, you can see it is moving from one end to the another. So even though the laser reach the end part, there is some amount of the temperature is maintained here. That is the beauty of the simulation. This is how you have correlate the results with the experimentation. Clear? And so this is one of the simulations that we have performed in the laboratory. This is how the is speaking at the center of the beam mark, something around 5000 degrees centigrade. After that, you can incorporate with the MATLAB and you can find out the temperature distribution in different load steps. And the same thing I utilized using the COM package to show the capability of console as well as the answers as well as the abacus. You see, this is that how the heat source has been fitted on the circle. Something about circular profile that is also possible doing with the simulation, and how the temperature is distributed is beautifully provided here. You see how beautifully you can understand the process, you beautifully can simulate the process. And not only on this type of simulation, but you can use it for additive manufacturing. So when you go for this wire and additive manufacturing, you can build the filler wires, you can deposit the filler wire on the substrate material, and each and every layer will be placed one over the other. It is a layer by layer technique, and you can use your element birth and depth options for simulating that process. Yes, sir. And I want to thank my scholar, MS scholar, Mr. M. Arun Kumar, who beautifully simulated the process by using the element birth and depth options. And this is the wall which has been created, and we have a very beautiful facility at our laboratory. And with the guideship of my mentors, Gunashekaran sir, VB sir, etc., etc., we have developed a beautiful laboratory, and we are doing lot of additive manufacturing, especially on different materials: 347, 321, 304, 316L, etc., titanium, aluminum, etc., etc. And this is the base paper which has been utilized by me for simulating how birth and depth options. I think it is not running now. Okay, now it is running. See how we are simulating the additive manufacturing process, and this is something taken on from the literature, the bottom one, where when you are going for additive manufacturing, you can simulate, you can do layer by layer additive technique, but because of this overheat input to the model, stresses will be induced on the substrate material, and it leads to the distortion. If there is a high distortion level, then your product will not be in acceptable stage. So we can do a number of simulations and find out the exact process parameter which will provide a fruitful results with minimum distortion. That parameter will be used for doing that product development. Clear, sir? And so many things are available. I am not making out my study for one particular thing, sir. So I have different simulation for doing the butt joint configuration and even the heating tail. This is also you can do for different welding speed, how the heating tail will move. So what is that? It is something about a preheating zone, and we have a very high tail, because when you go for a very high interaction rate, you are getting more and more temperature distribution on that material. That's why your heating tail will be elongated along the moving direction at the very low welding speed. Okay, so it is not only on one configurations. I have tried on the different lab joint configurations and find out what is the temperature distribution and what is the effect of process parameter on different joint configurations, and I have been validate the results with different joint configurations with not only the lab but and also for the T joint configurations, how the temperature has been distributed on both the side. That also we have experimentally we have compared all the results, numerical simulated results are validated with all the experimentation. See, and this is some of the simulations to find out how the temperature is distribution only with respect to the molten pool. The blue color things I have showcased in the video, same thing that you can do it. So if you take that molten pool alone, that also you can use the simulation here, and also this keyhole. Keyhole also we can do the simulation here. See, it is above the vaporization state. Like you can take only the isotope related to the vaporization state, and you can perform the simulation. And you can compare the results. And this is another beautiful thing. As I discussed with you, there is a paper literature is available that they have used the different beam power with different welding speed has been impinged on the GG17 glass material. As I have discussed with you, I have used the COMSOL as well as ANSYS for simulating that laser beam welding on glass material, that I have compared the simulated results with the numerically with the available literature for different process parameters. Okay, so these are all the things. So whatever may be the thing, first you have to understand the physical phenomenon of the process, find out what you mean by the process, why you have to do the simulation, then adapt the proper assumptions, apply the boundary conditions, loading conditions, simulate the problem. Okay, so these are all the references that I have referred. Without these references, it is highly difficult for me to make this presentation, to present this presentation to this forum. And I'm extremely thankful to Rajakumar sir as well as VB sir for giving me an opportunity. The time is very short. I have prepared the presentation for 3 hours. It's very extremely thankful to the participants who are patiently listening my lecture. So if you have any doubt, you please come back to me. It's my pleasure to answer your queries. Please.
Thank you, sir, sir, for giving a nice lecture on simulation part. Participants, if you have any doubts, please interact.
So if you find time, because 1 month back we have used our Abacus welding interface module for simulating the friction stir welding process. You say that I am showcasing through this forum. It is not published yet. You see, something about the advancing side as well as the retreating side, and the tool is entirely plunged into that material and do the stirring actions, and with the capability of the Abacus. And I want to thank my scholar Pramod, who have made this presentation, who have made this simulation in a beautiful manner. So now the session is open to audience. Any queries? I think Professor Sharan Raj raised one query. What is the query, sir? Please, sir. Now you please open your mic and speak to me.
Sir, good morning, sir. Sir, actually, when we perform the finite element analysis, especially when it comes to the convergent criteria for meshing part, so how to generate graph errors?
Great, very good, sir, very good. Especially it depends upon the problem that you are going to do the simulation. Now, coming to the part, what I'm going to give here. One second, I'll just coming back to the presentation. I'll explain it with my mesh. See, here you see the mesh model. What I have showcased to you, I have discretized this model. I think 1, 2, 3, 4, 5. So 5 elements along the thickness direction, and I think now it is clearly showcased to you. So 5 elements along the thickness direction and 20 elements along the width direction. Sir, how you could achieve this element? See, first randomly you have to select the size. And the size of the element that I have selected based on the spot diameter of the beam. The spot diameter of the beam kept for the analysis is something around 0.8. So minimum I can keep something around 0.1 as the element length as well as the element width. Correct, sir? So element length as well as the element width, it should be of 0.1. Even if you go for 0.2, you can work in a better way, but the refinement of the results, it is very difficult to get the refinement of the results. So in such cases, what I have adapted, I have started from 0.1 as the minimum element size that I have utilized for the meshing. And first I have kept 3 elements along the thickness direction. I have carried out the simulation. In that I have find out what is the temperature, what is the peak temperature. So element numbers, the x-axis, peak temperature at the y-axis. If you draw a plot between the element numbers as well as the peak temperature. So first 3 elements, so you are getting 1 temperature. If you keep the 4 element along the thickness direction, you are getting another temperature. If you are keeping 5 element, you are getting another peak temperature. If you are keeping a 6 element, you are getting another temperature. So if you join a graph, you see, even you are enhancing the number of elements along the thickness direction, but you are not getting a very peak temperature. Correct, sir? So you are getting out the some peak and you are getting out some fall in the graph. So in such cases, you are finding out some optimum value. So keeping 5 elements along the thickness direction will produce a less computational time, and also I could achieve a good temperature value. Correct, sir? So this is how you have to do the convergence study. Clear? I think I have appropriately answered your question. Clear?
Yes, sir. Yes, you're right, sir. You're right, sir. Thank you, sir.
Thank you. So this is only for a simple case study. When you are going for incremental sheet metal forming, and also when you go for metal working operations like that, you have to do the discretization along the thickness as well as along all the 3 sides. You have to select the material, select the element size, X, Y, and Z. Thank you. Okay, simulation of welding with soft test. No, it is not, because I am not advertising any finite element packages here based on your availability, because Abacus is available. Availability of the software is very, very important here. And in Abacus, there is number of things you have to add. So you have to install that Fortran compiler. You have to introduce Visual Studio, and you have to add that Abacus welding interface. These are all the things that should be added. Then only you have a comfortable to simulate the problem. It depends upon the problem. If you go for large explicit type of analysis, like a metal cutting operation, then you can depend on Abacus. Sir, I want to do something on crash studies, crash analysis, then you can depend on LS Diana. Sir, I do something on, irrespective of the mesh, I want to make only a little amount of work in that, then you can go for that ANSYS workbench. So it depends upon the problem only how to utilize the finite element packages. It is not like that use Abacus for all the problem. No, use ANSYS for all the problem. No, ANSYS LS Dyna for all the problem. It's not like that. So we have the familiarity of using that ANSYS, Abacus, COMSOL for simulating the welding processes. Okay. I think Venkateshwar, I have appropriately answered your question. Ankush, is there any resources to understand the simulation process, step-by-step welding joints like lab joint, bed joint? Yes, it is available with me. So you please note down my mobile number. I think it is available to all. My mobile number is 944364928. People call me Siva, even though my name is Siva Shanmugham. People call me Siva. Anytime you can put a query to me, I will answer to your question appropriately. Thank you. I think I have answered your query appropriately. Venkateshwar, once again, is there any theory to design number of elements in simulation of welds? I think I have answered this query to Sharanraj sir. Like that, you please open my video once again. It is recorded video. You please open once again and get more exposure in selecting the element size. Sir, Manivandan sir, has any simulation work has been done on friction surfacing? It's a beautiful question. I am anticipating this question. Still now it is not there. I think Rajakumar sir has also raised this question to me 1 month back. Still it is under progress. Soon I will provide solution to your problem. Thank you. John Rajkumar sir. One second. How many welds on bead-on plate weld? No, it is bead-on plate weld. You are not going for in-depth characterization study. Depends upon the availability of the material. You can do the simulation. You can do the experimentation trials and find out only the temperature distribution. Find out only the weld bead geometry, size of the weld bead geometry. For predicting only, for measuring the weld bead geometry, you are doing only the bead-on plate trials. If you are doing an in-depth characterization study, you have to depend only on the butt joint, not on the bead-on plate. Bead-on plate trials is only for understanding the effect of process parameter. Preliminary. It is only for preliminary studies. If you want to fully exploit, then go for the butt joint configuration. Purnima sir, please sir, please.
So I'm Giridhan speaking.
Yes sir, please.
Giridhan speaking. That regarding what about the heat effective zone? You can able to predict heat effective zone by this temperature distribution.
Very good question. See, as I want to plot. See, if this is the graph between the distance. No, I think I'll use D in the x-axis, temperature along the y-axis. Sir, this is the joint, and this is the weld bead. Correct?
Yes.
This is the weld bead. See, you have to pick the temperature value along the width direction and along the depth direction. So you are getting a two graph. So along the depth directions, what will be the graph? This will be the graph. Sir. So you know, as indicated in the presentation, the melting isotherm is something about 1450 degrees centigrade. For example, this is the 1455 degrees centigrade, and you have to draw a line in such a way that will interact this curve at this point. So automatically you are getting out the x-axis. For example, this is 1 mm. Either side, because this 1 mm is something about the depth of penetrations. Above that, this is full of melting isotherm. Below 1455, it is still in the solid phase. It is not giving the melting isotherm. Sir? This is related to the depth of penetration. Similarly, if I am drawing a plot for along the width direction, so this is distance, this is temperature. So this will be the graph. And the same thing, 1455 here. And this will be the 1 mm this side, 1 mm this side. 2 mm is the width of the weld beam and 1 mm is the depth of the weld beam. Like that, you know the heat affected zone. What will be the heat affected zone? It should be greater than that of the recrystallization temperature. For a stainless steel, it is something around 825. If you take the plot between 825 to 1455, the area which is encompassed by this location, it is called the heat affected zone. It is an approximate value. Correct?
Okay.
Okay. Thank you. I think I have answered your question appropriately. Correct, sir?
Yes, okay, but I think you may also look at includes material property also, based on material also.
Yes, yes, because I have used the temperature dependent material property. I think you could remember that. You could remember that the non-linearity, what I have considered is something about the material non-linearity. It is clearly given in that flow chart. It is given in that flow chart. See, this is a flow chart I have showcased to you. The temperature dependent material property.
So
You have to take up to the 2500 degrees centigrade. Then only these things are valid. Otherwise, you will not get this one. Thank you, sir. One of the best presentation that I have come across. Thank you, thank you, thank you. I will answer your query for simulation of friction. Kindly suggest textbook to explore more on FE simulation of welding. I think physics of welding one book is that. I forgot the author name. I'll get back to you, sir. I will get back to you.
Lancaster, I think. Lancaster, I think.
Yes, sir?
Lancaster. Physics of welding.
Okay, physics of welding. Yes, yes. Please, sir, please type the information in the chat box, sir. Others can get the benefit of the thing. Very informative session. Thank you, Karnagaran. Thank you, sir. I will give more information related to the FE simulation of welding. I have another 2 books, sir. I forgot the name of the books. I will get back to you. Any other queries? Any other query? I think I have crossed the beyond the stipulated time. Extremely sorry.
Yes, sir. Not an issue, sir. Sir, actually, now the participants can understand how this simulation part is like a ocean. We cannot complete it within an hour or a day.
Yes, yes.
I think you have answered almost all the questions, sir. The session was excellent and informative, sir. You have covered all the basics. You have covered all the basics parts, sir, which is very necessary for the beginners who are entering into the simulation part.
Okay, okay, okay. Thank you for giving me an opportunity. Convey my regards to VB, sir. And
definitely,
thanks
sir.
a lot. Thanks a lot, friends. We will meet in some other occasion. Thank you. Thank you.
Yes, sir. Thank you. Thank you so much, sir. Participants, in another 10 minutes, we will start the next lecture.
Shall I leave the meeting call, sir?
Yes, sir. Yes, sir. You can leave, sir.
Welcome to all. It's a great honor to introduce Dr.G.Vimalan sir. Mr. Vimalan obtained Bachelor of Engineering in Metallurgical Engineering in the year 2001 from Government College of Engineering, Salem. He obtained a postgraduate degree in Materials and Metallurgical Engineering from Indian Institute of Technology, Kanpur in 2008. He completed his PhD in the area of welding metallurgy in Department of Metallurgical and Materials Engineering in NIT Trichy. Currently, he is working as Deputy Manager in Welding Research Institute in Bharat Heavy Electrical Limited, Trichy. His research interests include welding metallurgy, gleeble thermomechanical simulation, failure analysis, and residual life assessment of boiler in thermal power plant. With this introduction, I welcome Dr.G.Vimalan sir to take over the
Thank you,
session.
thank you, sir. Thank you, sir. Good morning to all of you. First, I would like to thank Annamalai University Organizing Committee for providing me this opportunity on this faculty development program. Okay, I will start my. So this session is about R&D studies using gleeble thermomechanical simulation. The contents will be such that we will be seeing first the brief description of the gleeble equipment and what is about physical simulation and what are its capabilities. Then one by one we can see the case studies we have conducted at the Welding Research Institute B.H.E.L Trichy. Many studies we have been conducted, and these are some of the main work. The first one we will be seeing about the grade 91 post-well heat treatment simulation. We will be simulating post-well heat treatment, how to find out what happens in case the temperature is exceeded unknowingly for various reasons. Then we will be seeing a CCT diagram, we call as a continuous cooling transformation diagram for coarse grain heat affected zone of another boiler grade material, SA106 grade B steel. Then we will be seeing about we will be seeing a normalizing tempering simulation behavior in grade 23 panel after hot bending operations. So next we will be seeing upset welding of joining of titanium and stainless steel. It's a kind of dissimilar joining. This dissimilar combination is difficult to join actually, but we have attempted in kind of upset welding using this gleeble equipment. Then we'll be seeing another heat treatment simulation of high strength plate. They are being used for defense application, and this material has been customer who has been given a feedback. They have been observing poor properties in toughness, and they have been reported us and to solve workout. So that also we'll be seeing. Then we'll be seeing about hot cracking studies. It's a kind of weld hot cracking in a new material in 617 SMAW welds also will be seeing. And another one is time transformation. We call as isothermal transformation diagram. A TTT diagram will be seen, another boiler grade material. In time pyramids, I will also go through next two short-term stress relaxation testing and hot compression. That depends on time, how the time is available. Then we'll be seeing that. Physical simulation is an reproduction or a replica of the real world situation in a lab, small lab scale, laboratory scale actually. That is what mean by physical simulation. Because if you do any experimentation, the real production product, that will be very, very costlier. And it cannot be again used for a real one. It will be cut in case it may require a kind of many experimentation if you want to in a real, that will be a very, very costly, and will be wasting enormous energy, money like that. So physical simulation, we are not wasting the real product, but same time we'll be doing we want to simulate the real thing, but in a small lab scale. That is what we are using a gleeble instrument. The data obtained will be very useful to solve the problems. We'll be encountering any product preparation or manufacturing. That is what I meant by. This is what the instrument we call as a gleeble thermomechanical simulator. This has been supplied by Dynamic Systems Inc. from USA. We have been commissioned this instrument at WR Welding Institute in the year 2010. Since then, we have been working continuously on various projects. You can see that This is what the simulation chamber will be. The specimen will be kept at the center. It may be a different type of specimen you have to prepare, a 6 mm cylinder or 10 mm cylinder or 11 mm square, like that we have to prepare. This is heating happens by a kind of a direct resistance heating. The system supplies a very high high energy current. On its own resistance, the material is heated. So only the conductive material will be easily conducted. Otherwise, you have to coat it and then you can conduct a simulation like that. You have to do. So here you can see all copper type of copper alloy grips will be coming. The kind of copper grips. 4 numbers will be coming each, and after then you have the clamps will be tightening will be used for it. So the one jaw will be fixed in the right side. This left side part will be able to give you tensile or compression, or this will be connected to the RAM actually. The load can be applied. You can apply a 10 ton in load and tension or compression like that you can apply. And there is the middle portion, there is a dilatometer is coming. So that will be, if you want to, the diameter wise changes, whether it may be expansion or shrinkage, you can measure in the micrometer level. That will be placed with this. And temperature you can measure. There are 4 boards at the time. Thermocouple wires can be connected at the middle. That also image also will be showing in the next images. There will be computer program will be there. You have to what you have to prepare it, what temperature, what strain rate, and what strain level, and what are things you have to want in the product like that. You have to simulate. You have to make a program, and then the specimen also will be you have to fit it in the chamber. That you can fill it with argon so that it will not go for oxidation or problems like that. While heating, it can happen. So you can fill it with argon and stop it, or otherwise you can also have access to a vacuum. So 10 power minus 5 liter, you can at least minimize this kind of oxidation problem. So the specification of the instrument such that it can go to maximum heating rate 10,000 degree per second. So it means that you can reach 10,000 degree in 0.1 second, very high heating rate. Stroke rate is kind of a strain rate actually. It can move 1000 mm per second actually. And the distance it can move is 100 mm, the maximum stroke. The force it can apply 10 tons in both tension and compression. The control methods, how you can control, you can use stroke as distance or force mode or a lengthwise change, that we L gauge we call as a diameter change. Also we can strain or stress whatever you can use it. The specimen size will be such that you have to use a 6 mm diameter as a round specimens, or 10 mm round, or 11 mm square. This kind of 11 mm square will be used. Further you can machine it with 10 mm, and then you can use for toughness testing. Charpy V notch will be taken at the middle, and you can go for toughness testing. Otherwise 6 mm cylinder sometimes they can use with, if you have a threaded, you can go for a tensile or tensile like that. Otherwise you can see for microstructure. Otherwise flat sample also is possible. You can use a 2 mm with 50 mm square sample, that flat samples, that also possible. So next we'll be seeing what are the testing is possible with this instrument. We can do a hot or a tension testing. It's a kind of where you can do high temperature tension testing, or from you can go up to 1000 water, depends on thermocouple. You can go 1000 degree or different temperature or tensile testing. And similarly you can go for a uniaxial compression, or there is another variant, plane strain, that will be useful for hot rolling process. That is also both compression test can be conducted. And another is a strain induced crack opening, that will be useful if the material you can it's a kind of testing. We have to compress it actually and see the any cracking is coming. A kind of testing is possible. Another thermal fatigue or thermomechanical fatigue. You can apply a load with it at the same time temperature, or only you can apply a load and see the mechanical fatigue. And the creep testing you can again stress relaxation testing another, but these are tend to be very costlier, but why you are going for long run. But you can do a stress relaxation type of studies. And another thing is for hot cracking studies, you can do a combination of nil strength temperature with hot tension test. That will be helpful for hot cracking, weldment hot cracking. That's possible. Next, using dilatometry, where it's a very high resolution dilatometer is there, and using that you can construct both TTD diagram or a continuous cooling transformation diagram, time temperature transformation diagram. Both is possible. You can any phase transformation you can do, that also possible. Then melting and solidification studies, liquid empritment studies, solid liquid interface studies, everything is possible. In process, you can do a continuous casting, which has been the steel product mostly now is been produced the continuous casting process. That is possible with this instrument, and Musizone, a kind of solid liquid mixer processing is possible. Hot rolling simulation, forging, extrusion, all hot working process we can simulate with both. We can strain the effect of strain, effect of temperature, effect of strain level, strain rate, all can be optimized with these simulations. Then weld heat affected zone that is what the main experiment initially. Then it was been developed for all other process. A kind of diffusion bonding is also possible, where two specimens will be polished with metrography. Then you can bond it at high temperatures. Possible heat treatment, whatever you can do, strip annealing studies or normal whatever heat treatments is possible. Upset welding is possible. Powder metallurgy studies also possible. You can see that how the programs are being made. The first, the mechanical, you have to specify the particular mm. So you can go a compression or a tension like that. In compression, you have to put a minus, and then what this is the first point is about time. What time you want to make that kind of a movement, and what temperature you want. You have to specify. Both you get possible with centigrade or Fahrenheit like that. You have to mention it. So whatever your program, you can keep on writing and then complete. So at the same time, main thing is that when you started running the experiments, it will show what is the strain level, what is the temperature. The panel will display all the factors. So you can while running also you can able to see them in the panel. So before simulating, you have to each specimen has to be welded with thermocouple welder. So the specimen 6 mm cylinder, you can take it. Whether you mark it the middle point, two thermocouple we call as a chromal aluminum type that can be simulated up to 1000. Maximum operating temperature is 1250 actually. So your two thermocouple will be welded in the transverse. Actually, the gap may be less than even 1 mm. You have to weld two wires with the help of this thermocouple welder. So this temperature maximum based on thermocouple K type, you have to go up to 1250. In case of S type, platinum, rhodium versus platinum, you can go up to 1450. And R type also platinum, 13% rhodium versus platinum, that also similarly 1450. And B type is the maximum, you can go up to 1700, where it has 30% rhodium versus 6% rhodium platinum combinations. So you can see that they are using a different kind of grips actually. We have a square 11 mm square full contact copper grips actually. This will be used in the middle of simulation chamber. 4 numbers will be coming. They will be giving a supplying high heat. The middle portion will be kept to open out actually. That we call as a free span. That is where the actual simulation will be happening. So if you want 1000 degrees centigrade, the middle portion will heat. There will be always a thermal gradient will be there. Middle point will be same. The simulation point. The 1 mm away from both the middle, there will be temperature drop will be there. We call it as a thermal gradient. And just where it is touching, it will be again. It may be maybe 100 or 200 degree. It will be lower. So it will be different for different materials, a different kind of combinations. There will be a different kind of 6 mm round will be given, 10 mm will be given. So you can select whatever your requirements like that. So again, there is another type of grips also is there. They have a stainless steel. This copper able to give you very high heating rate and cooling rate. So copper because of high conductivity, they can give very high fast heating also or cooling also possible. But in case of stainless steel grips, it is not so actually. You can see the the thermal gradient will be very flatter. But in case of copper, the thermal gradient will be so whatever the process you have to the selection will be very you have to appropriate process you have to select. So there are different we call as off contact copper grips, again a 4 mm contact stainless steel grip. This will give minimize the thermal gradient. So it will give you uniform temperature along your length maximum. So it may not be even maybe the difference will be you can minimize in the 30 degree or 20 degree like that. So another capability is the quenching. So you can use water quenching or you can go for air quenching. There are tanks out there, you have to fill it, and with this provision you can able to increase the cooling rate. In case you want to conduct any quenching experiment, you want to cool it very faster from high temperature, you can supply water using this provision. So in case you want a moderate, you can also still you can able to with air you can bring a moderate cooling. So if in case of the experiment, normally even without this also will cooling will be coming, but what are the cooling rate you want you have to use appropriately. So another factor is we call as a thermal gradient. The temperature at only at the middle point it will go to the requirement of our simulation. If you want 1100 degree, the middle position will be there. But if you come 5 mm away from the center, there will be drop. In case of this one, the bottom one belongs to actually copper grips. If you want to full contact copper grips, the temperature will be again 100 degree lower for 5 mm per. And again, if you come again 15 mm, it will be enormous difference will be there. It will be close to the 250 or something. So it will be suitable. This copper grips will be suitable for welding kind of heat effector zone simulation or type of other things. So if you want to do hot tension type of testing, you can select SS actually that we call as a hard job. There the gradient will be very minimal. So when we maybe 10 to 20 degree there will be there. Middle position overall the middle free 30 mm free span will be almost suitably. Then it's an off contact grips will be in the middle level of these two. Again, as I told earlier, the copper grips tend to heat and cooling also will be maximum. In case of you see the SS grips, cooling rate will not be that much actually. It will come slower. You cannot expect. So if you want to cool very faster, you have to select copper. If you want moderate cooling like that, you can go for SS grips. So first our simulation and the grade 91 post-volley treatment simulation. This kind of a grade 91 is a kind of material used for power boilers. We are using for headers and different superheated tubes like that. And actually this one it will be a temper martensite structure with M23C6 carbides and MX carbonitrates will be a second considered in the form of second phase will be there. So generally irrespective of all thickness forms, they are actually once they are welded, they are compulsorily subject to post-volley treatment. So because of this temper martensite structure. So as you know, in a heat affected zone, you will get a fresh martensite. So they are typically conducted with post-volley treatment 760 actually. Generally, this 760 is arrived by AC1. By AC1 is lower critical temperature, minus 30 to 50 degree lower. That is what is been code as representing. So as per this material, all the ferrite stabilizers tend to rise. Chromium, moly, vanadium, something like that, and austenite stability tend to lower. So generally, in case of base metal, if you consider the weld metal, there will be change. Difference will be there in the alloying element of nickel and manganese, because nickel and manganese will be in base metal will be less than 1% support. Typically, they will be in the 0.6 or 0.7, but in weld it will be higher, because weld metal tend to need to have high strength, so they will tend to have higher nickel manganese. So same wise, with this alloying tend to lower this kind of AC1. So in many situations there will be chances are there the post-volley treatment 760 in the furnace they are doing it, there are many chances you can raise it above 760. They even go to 800, 820 like that. There are situations coming, and again same they can also go lower. So this experiment is such that what happens if it is rising towards AC1, that is a lower critical temperature. That is what we will be seeing in this experiment. So the AC1, we can, the ASTM standard 1033 will specify how we have to determine AC1 temperature. So we have to heat it up to 700 degree at the rate of 10 degree per second. Then after 700, you have to put very, very slowly. That you have to go by 28 degree per hour actually. So you have to do maybe a 9-hour test duration is required. You have to do very slowly. Then you have to find the change in dilation. That is what the linear strain. Generally, any metal heated will be expanded, but once the transformation point is reached, it will actually decrease because of the phase transformation happening. And again, after once it reaches the AC3, again the linearity will continue. So the change in the linear portion, we will be putting a tangent, and then we will be finding the AC1 and AC3. So again, many researchers also have developed empirical equations based on the chemical composition. So different researchers from USA Santella, they have based on the chemical present, they have been presenting the equations. That is also we can appropriately you can check it with AC1 for weld metal or base material. So this typically have been welded pipe, P91 pipe, and then with 30 mm thickness, we welded the S-material process with Vogler weld, and then we have taken where the weld portion will be at the middle, specimen will be extracted. The 10 mm cylinder is extracted, and with the length of 86 mm length, and thermocouple is welded, and this is what the dilatometer. So where the center, the specimen will be coming here, this portion, and while the heating and cooling, this spring will be there, and it will able to measure online live and the level of micrometer. So how much the material is expanding during and how it is sinking. So this is a standard, we call as a standard setup, standard jaw like that. The specimen, the thermo after thermocouple we can is welded, and then we place dilatometer also is placed. So the plan will be such that we will be simulating for both the base metal and weld metal, and we will be going first we will be going normalizing actually. Then we have to normalizing will be generally conducted at 1050 degrees. Then our post-weld heat treatment is coming. So post-weld heat treatment will be slowly rising from 760 to 780. Then we will be closing slowly. Will be closing to the AC1 level, and then the heating rate will be 0.5 degree per second, and then in condition 2 will be heating at a very slower actually. This is what actual product will be doing at slightly 200 degree per hour like that. Will be cooling also will be higher, slightly higher. It will be slower actually. In actual, we are not doing because of reduce the distortions. We are doing at a very low as per code actually. So then same time we will be measuring the dilatometer and microstructure and hardness. Then we will be correlating all the so this is what we have to do. The temperature time profile will be going at 700 very fast. After that we have to heat very slower, 28 degree per hour. You have to keep it, and then this is what the chemical base metal, weld metal. So the base metal will have nickel and manganese 0.6 almost, and weld metal will be having a higher actually. So that what typically will be coming. So the experiment such that we will be simulating normalizing for at 1050 at 10 minutes. Then we will be going for a post-weld heat treatment at different temperature. In case of weld metal, we will be selecting a difference of 760, 770, initially after 20 degree. After that, will be 10 degree increase will be there. So 800, 810, 820, 30 like that. In case of base metal, we will be doing at 793, 830 like that. It will be slowly 10 degree will be raised actually. So in experiment 2, they are actually doing at a slightly slower heating and cooling rate, that fast per ports. So first we are measuring AC1 for base metal. The AC1 is almost 822 degree. In case of weld, actually it is 792. You can see the curve. This experiment conducted in just a heating method. You have to heat it and then find out AC1, AC3. So this is what the different dialitometry plots for different temperature. First for 793, first it goes like that. It is from low temperature. It is for first you are doing normalizing at 1050. So the expanded material tend to expand up to HE1. After that there will be a drop will be there, and after once it reaches HE3, again it will be in continuing the linearity. So it will go up to 1050, and then we are quenching actually. We are quenching to room temperature. And then while quenching, you can see there will be transformation of MS. That is what almost 400 degree. And again, we'll be seeing MF, martensite finished transformation temperature. Once it comes again to room temperature, again we will be going heat treatment for normalizing, tempering at 793. So again, you can see the linearity. There will not be any change in case of base material. There will not be any significant change up to 823. So all the plots looks very similar. You cannot see able to see. So it means that you are getting a complete temper martensite. So you are while normalizing, you are getting a martensite, fresh martensite. While tempering, the structure turns to temper martensite. In case of 833, there you can see it. After normalizing, it will be same for all experiment. Then it goes for straight line to up to 833. While it coming, you can see there will be a dilation, transformation at a very high temperature, 800 to 700 degree. There the phase transformation is seen. That is what the encircled here actually. Then you comes to the room temperature. So again, 843 centigrade. Similarly, you can see up to normalizing is okay. Then while tempering at 843, you can see while coming, you can see a distinguished transformation at 800 to 700. There is another while coming again further. There will be another transformation. You can coming at 416 to 341 degree centigrade. So the higher will prolong. This is been corresponds to ferrite transformation, and again this is corresponds to martensite. That is what come normally at this temperature range. Again, in 853 there is significant equal portions is coming. That both are being encircled. You can see. So this is what all the temperature AC1, AC3, MS, MF, and FS ferrite start temperature, ferrite finish, martensite start and martensite. While during this is during the heat treatment, this is during the normalizing. So what you see is up to 823 only you cannot see only straight portions are coming. So it means that only you are finally getting a temper martensite. But in case of 833, that's a transformation is seen. So that is what the ferrite transformation is seen. 843, 53, both the transformation, ferrite and martensite are being seen actually. There is a that is what the temperature. And you can see almost the main part, the AC1, the trend is almost same actually. In all experiments, 853, 847, 850, 51, like that. It almost, even though it won't be exact, but the range will be within 10 to 15 degree. And again, AC3 also the trend is coming. And the MS, everything, the trend has been followed actually. This correspond to weld metal actually. So this weld metal temperature actually 770. Again, this again normalizing cycle will be same. After that, you can see only straight lines, the heating portion and the cooling portion. But in once it is 790. There will be marginal, very small dilation is there at very close to 740 degree to 665. That is what. But in 800, it's very, very clear. There will be a change of dilation is coming at 750, almost 660 degree, and another dilation is coming at 484 to 400. And keeping again rising to 810, a significant transformation will be seen at lower actually. you can see a significant the change of dilation strain again represent the quantity of transformation. So once the strain is lower, the quantity will be lower. Once the strain level is higher, the quantity also gets higher. Again, 820, 830 are given here. In case of 820, there's a marginal at 750 to 670, but significantly you are seen at 480 to 335. Again, in case of 830, only you're full of martensite, almost 90% you see about at the 424 to 300 degree. So this represents martensite transformation. So again, a temperature has been given for similar to what we have conducted for base material. So again, you can see again the AC1 are slightly lower range for weld metal. So 819, 820, 824 like that. Only one is coming, but other very closer, and AC3 are and MS also very closer. And that is what other Farad. These are all secondary transformation. We call as a secondary transformation during that happen during tempering process. So microstructure we have taken, and we can see this kind of a this is we call as a temper lathe kind of structure. Temper martensite where the carbides are been and MX carbides and M23C carbides are embedded in the matrix. So typically will be coming, but in case of base material, when temperature is 833, there's a kind of carbide segregation along the pre-rusted grain boundaries. You can see it. But once it is 843, you can see ferrite, polygonal ferrite will be seen in the FM as a fresh martensite that all been visible. So in both you have 843 and 853 will be seeing like that. In weld metal, in case weld metal, this is actually very finer actually. Structure is not that much able to clearly see it in the optical. But 800, similarly you see a kind of a lathe structure, but 810 we can able to see a part of tempered martensite partially tempered, and others are untempered. And again you can see the grain boundary are tend to form at higher 810 actually. Grain boundary are there tend to be migrating grain boundaries are forming. In 820, 30 and all, the structure is finer, but again in 830 you will get the carbide quantity has been reduced, but again in 820 also the level will be segregating to the grain boundaries. Rusting grain boundaries has been segregated. Again we confirmed in micro harness also this is kind of high harness represents the martensite kind of structure. So hardness, you can see this is bulk hardness. Once the temperature it's been raised for in case of weld metal, there is a hardness will be rising actually. This is because there will be a lot of martensite formation in weld metal. But in case of base metal, it's a kind lot of ferrite is coming. In case of once the temperature rises close to the AC1, you are getting a lot of ferrite with some kind of quantity of so your hardness is lowering actually. That is what the reason. But it was initially it was very close to 220, 230. But once the temperature is rising very closer to AC1, only in case of weld metal it has been rising. But in case of base metal it is not so actually. The pre-roasted grain size also we measured, but slightly it has been grain sizes are been trend is not that much. Once it is dropping and then slightly increase will be there. In case of base metal again rising and then dropping and then slight increase will be there. Again it's dropping. Okay, overall what is our thing is that our findings, the AC1 for weld metal of P91 and base metal, it is for weld metal it is slightly lower actually. In case of base metal it was very close to 822, but in case of weld metal it is 792 actually. So there will be a significant drop is because of this higher nickel. So this nickel and manganese almost 1.1% compared to 0.6, they are tend to drop this AC1. So that is what findings. And again In case of these post-weld simulations, you can see that there's a clear kind of alpha ferrite is coming in at 790 in case of post-weld treatment, that is SC1 minus 33. But this occur in case of actual simulations, actual product conditions, the occurrence is not observed at 800, slightly higher temperature, and this is because of slower heating cooling rate actually. So safe, what is the safe post-weld treatment will be 760, 780. That will be 30 degree less than SC1. That is what is again confirming. The experiments confirms that the safe will be 760 to 780. Once it is reaches 790, so there are chances that the ferrite can happen. So once ferrite is coming, your complete creep properties will not be obtained. So you will get a very good effective post-weld treatment only if you get a full of temper martensite structure. So any case of alpha ferrite or fresh martensite will tend to decrease the creep strength. So next we will be seeing about continuous cooling transformation diagram for post-grind heat affected zone. This actually the heat affected zone is in any weld is inevitable. So this will this post-grind affected zone represents once the peak temperature is above 1100 to 1300. So that is what we will simulate actually. First, what we are doing is we are take the specimen and thermocouple is welded, and then different temperature will be reaching 1200, 300 at the heating rate of 100 degree per second at 1 second dwell time. After that, we are cooling at different cooling rate. 100 degree, 50 degree, 20 degree, 10 degree, 5 degree, 1, and then 0.1. So there are two setups will be possible. One, this is what the earlier standard jaw. Actually, there's another setup is there. We can remove this one because the disadvantage of this standard jaw is that as it's connected to RAM, there will be a slight load will be placed on the once the temperature rises above 1000 or when the high temperature, it will RAM will pose some kind of strain. So that will be avoided in case of low force jaw. So this one is disconnected with the RAM, but only specimen can expand actually. So it will not disturb the strain will not disturb any transformation. So this will be preferable. We can go for CCT sample, but the specimen is slightly different actually. This one there are provisions are there for water cooling. Inside there are drills will be there, and you can it can go, water can pass at very high speed, and it can bring the cooling rate. The middle portion will be temperature will be heated. So the whole middle portion, the isothermal, you will get the same temperature. So it is what the quenching system is coming, and you can the dilatometer is placed at the middle portion. You have to place correctly because thermocouple also coming. So you can accordingly you can write programs, different programs like peak temperature and what cooling rate you want it. You can mention the correct timings like that. You can change the different programs, different specimens. So here the dilatometer results you can see at very high fast 100 degree cooling rate. You can see 1000 heated to 1200, and then we cooling. You can see one transformation at 411 and another transformation at 290 to 59 actually. In case of 50 degree centigrade cooling rate, you can see a transformation at 597, and another deviation is slightly deviating from the linear, and then it is going to 415, and then it is coming. So this one there is a it represents a transformation actually. So again you have to confirm. So on the same specimen will be go for metrography for confirmation of microstructures. So in 20 there is a significant first two transformations are visible. First portion will be very high, and then a small portion will be coming in next actually. So in case of 10 degree, there's only one transformation. The first it will be coming, and then it goes for complete of transformation. So all the temperatures are being noted where the deviations are coming. So in 5 degree also you can see slight changes will be there, and there is another peak has been rising like that. So 2 transformations are coming, and again 1 degree also you will see that kind of changes. So you can see that all the temperature, you can see it. In case of 100, you can see only that that are mostly will typical for Martensite transformation only. MS and MF it will be belonging. And in case of 50-20, there are both binite will be coming at close to 600. Once binite coming again, it will be going for a Martensite. But in case of 10 degree, it only a binatic transformation. But again, for further lowering, there will be Fahrenheit, significant Fahrenheit is coming at 700 degree, 770. And 1 degree it is going to 730. So then it will be going for a binatic phase. In case of 0.1, there will be Fahrenheit, and again there will be a pear-like transformation. That is what there will be a rise of significant rise will be seen at the 0.1 degree. So again, we have confirmed this also in the microstructures. You can 100 degree, you can see very, even though it shows only one full of MS transformation, but slightly one very small 1% will be there, but only the grain boundaries, binite phase are seen actually. But in case of 50 degree, there's a considerable binite is coming. The Martensite are very not able to etch. That is what we will see in a very white kind of phase. But still, lathes have been, some portions of lathe have been etched. But in 20, you can see a kind of lathe type binite structure with the Martensite. Equal amount will be coming. And in case of 10 degree per second, you can see the grain boundary ferrite binite structure. But in case of 5 degree, even though the ferrite is being seen in the dilatometer, but there are the forms are very different actually. We see a Whitman type of ferrite, grain boundary ferrite, but even in the grain boundary, we have some very small amount of pearlite are being noticed actually. So this is what, but the morphology can be very, very different actually. 1 degree there are Whitman ferrite, grain boundary ferrite, and then some small amount of granular ferrite, binite also will be noticed. And in 0.1 we will see a pearlite structure. Mostly the dark phase pearlite only, and the ferrite also is there. Very big grain size will be coarser as it comes at very slowly actually. So hardness, you can see once the cooling rate is rising, just because of our phases quantity is rising, it's linearly rising actually up to 1100 degree per. Okay, this is what CCD diagram. Mostly you have to watch it actually. This is a log scale in x-axis, in temperature will be coming in y-axis. For different continuous cooling will be plotted here using the software. And you can see 4 major regions. It will be where slower portions, it will be ferrite and pearlite. Middle portions, it will be binite, and that's narrow portions that will be a combinations of binite and Martensite. But once it is 100, you will see about only Martensite structure. So very hardness for 79. So hardness also given the below. So next we will be seeing normalizing and tempering simulations in grade 23 after hard bending operations. So this grade 23 is one of the material we've been using for boiler. It's a kind of a new material. After the panels have been prepared, once it is going for hot bending, they will be subject to re-normalizing and tempering. So our manufacturing people have reported that once it is been subjected to re-normalizing and tempering, the toughness property was very poor. So minimum as per the requirement, there are 27 joules is requirement. They will be subjected to test in the lab. So after many trials, our manufacturing group also they tried many experimentation, but they couldn't able to find why it is been failing. So they also reported lab that they also not able to solve. After that, they have given for our this gleeble lab, and we have make a program. So and we found out that again simple actually we are subject to normalizing and tempering. The main first the normalizing we are subject to different cooling rate actually. So it is start from 0.25, 0.5, 1, 2, 3, and 5 actually. We found out that the toughness property, once the cooling rate is more than 2, we are able to get a good toughness that around even more than about 150 joules actually. All the cooling rate is above 2 centigrade per second, we are getting above 150. But in case less than 1, even for some of them even 50 and even very low values have been reported. So this is we analyzed again the microstructure. We found out that once the cooling rate is lower, we are able to see a polygonal ferrite. So that is what it's been the micro below is given here. Actually, ferrite for ferrite, you know, it again will reject the carbides, and the binary tends to have an high carbide, and the material structure is very tend to brittle. So that's what been observed. So hardness, if you see it, generally people will take hardness value, but they couldn't see any changes. But the hardness was overall the cooling rate. It's that much the effect is not seen. It is very 200 to 210. It was almost seen on all cooling rate. But only we have to see the toughness. We have to see that changes. But once the cooling rate is higher, more than 2 centigrade per second, you will get a ferrite phase is not coming. Again, you will get a very the lathe type of binetic, very complete binetic structure, and again prior grain boundary also visible. This kind of structure you tend to give a very good toughness. So after this experiment, the lab manufacturing group also happy. They changed it actually to increase the cooling rate. So normalizing, once the whole panel is being coming out, even the shop also heated. So they have tried for mist kind of cooling with extra fans like that. Still sometimes your panel is not able to cool it faster. So once, because the huge furnace panel is coming out, so sometimes they once it's not even coming, not subject, even they can put it in the water also. So the whole panel they can put it in the water. So that is also able to give a better cooling rate. So that is also they tried it and they have been successful. And again, the whole after normalizing and water quenching, they will be doing in a tempering cycle after that. So next we'll be seeing a kind of upset welding for dissimilar titanium and stainless steel. So this titanium and stainless steel is a difficult to join material actually, but still some chemical industries and some kind of aerospace industry they are using it for some critical applications. Mostly the different process. One of them is diffusion bonding has been tried actually. Diffusion bonding, one of the crucial point is that it has to be metallographically polished actually, very fine polishing, and the contact to metal is been, if any gap, metal to contact of two member is very necessary. So if any gap or any profile is not good, you cannot able to join actually. So very critical, very strenuous metallographic procedure is required. So that also very even that small error can cause kind of lack of fusion. So and you will end up with poor property. So in this one we are not preparing metallography, but kind of small preparations metallography. You have to just ordinary milling with slight emery paper, 200, 300 is sufficient, but still they have some kind of unevenness will be there. But this upset welding will avoid the extraordinary metallographic preparations. But we have to weld 2 thermocouples in the same one end. You can choose either a titanium or you can select a SS part, and one thermocouple is welded very close to the edge, and another is even you can try very closer to the middle point. So just to tap what the temperature it is going actually. So you have to fit it in the same standard grips with the thermocouple. 2 thermocouples will be, you can even weld with 4 thermal at max actually. 4 thermocouples can be at specimen can be welded, and the temperature readings can be given and recorded. One will be controlling, another will be recording at other locations. So what we have found is we want to go for temperature of 1150 actually, but even you can see some portion of the melting was seen, and the temperature was another portion. Slide we have seen locations. We have seen the temperature close to 1225 actually. That is what we recorded actually. So to the one thermocouple, it's a kind of rapid heating actually. We want to heat it this 1150 in a matter of 10 to 12 seconds, and then we are cooling it another 10 to 15 seconds. So the experiment will be completing in 30 seconds only. So very fast, rapid heating will be done here actually. So microstructure, if you see it, you can is given here actually. One this part, the region 1 is a stainless steel portion, and the middle dark line will be interface. So the interface will have a kind of intermetallic. Mostly sigma phase are seen that we have been analyzed in TEM and also in SCM we analyzed and found out. But this 30 micron, the middle region 3 is a kind of a beta titanium phase. The original alpha, the pure, this is a kind of titanium is commercial pure titanium that tend to be HCP alpha titanium. So, but the beta titanium, once alpha titanium heated above 882, the transformation will happen to beta titanium, and the same is retained at room temperature because of very fast heating and cooling with 30 microns. But again, some kind of alpha beta titanium is also coming. This kind of lathe structure, they are representing alpha beta. That will be width will be 70 microns, and after that you will getting HCP alpha titanium. So that is our base material. And another image also I given base microstructure, and this is kind of waviness has been very good actually. In case of diffusion bonding, the waviness is very difficult actually, but this, as the material is melted and the joining and all very good actually. So even the gaps you are able to fill it actually. So we analyzed in the SCM and even in TEM, and the first portion almost 68% iron and chromium 89%, nickel 10% manganese. But in the region 2, 67% iron and same. But this kind of again we confirmed it is kind of sigma phase. Sigma phase is a slightly higher chromium. But the sigma phase again tend to be a brittle type of structure. But in the region 3, we got 86% titanium, and with iron, this is what again a beta titanium has been seen there. And the lathe structure again confirmed as alpha beta titanium. So titanium almost 92% with iron 7.6%. So again, this kind of chemical at different points also is given here. So how the matter has been diffused from this side to that. So hardness and tensile also we have conducted. Hardness of our stainless steel part 232 and titanium 140 like that one. But in this kind of beta titanium, alpha beta, the hardness are higher slightly. So it raises to 300 to 40. But tensile test we have conducted it. The yield point was 240 and UTS was 274 like that. So, but you are not getting any elongation. You are getting very, very small, 0.4 or smaller. And material is, even though it's brittle, but your tensile property is somewhat you are getting on par. Some 70 to 80% of the best material we are getting actually. So next we will be seeing another heat treatment simulations in another high strength plate. This high strength plate they are used for kind of a defense type of application where bullets will be fired, and this material will have a very high ballistic strength to resist the kind of firing. So these are kind of plate they have been pressed actually at hot pressing, and then they have been product is been made. So that is what the process sequence. Again the same problem. They have reported what the customer reporting is that they are not getting able to meet the toughness requirements. So they are getting very uneven. Sometimes they are able to get good toughness, sometimes they are not. So they wouldn't be able to find out why how it has been coming. So again the problem is referred for us, and we have experimented for this problem. So again the same process. The heating will be conducted at austenizing region 900 950. Soaking will be 1.5 hour. 90 minutes to 1 to 2 hours, and after that pressing it will taken, it will be pressed in the hot press, so that will be conducted in 10-15 seconds. After that pressing is conducted, we have to move to the quenching tank. So that is what the figures also it has been given here for you. And cooling time 5-6 minutes, and you can see the requirement is such that we need both hardness properties. Hardness will be 290 to 40 BHN or 300 is okay, but both the toughness also a requirement. So there will be a toughness requirement to be there. Toughness will be such that we need a minus 40 degrees centigrade. We need 59 joules actually. That is for Charpy 3 mm U notch. That is this is a typical requirement actually. So this is what the requirement. So this material is a type of low alloy steel, chromium 1.5%, moly 0.3, nickel 1.1, and the carbon also is slightly higher 0.3%. So that is what the materials very high strength. UTS will be 981 and yield point more than 883. So thickness of the plate is 45 mm. So we done a CCD diagram. Our idea is to do a CCD diagram and also change the heat treatment, the real what they are doing it, and we modified. We understand the problem and we modify the same the heating schedule actually. So what we have done is same. We have do a CCD diagram first, and again for toughness we have to do a square specimen 11 mm square. You have to take it, simulate it, and then we putting in the again toughness testing can be conducted. So we have to do simulations and different specimens. First we found out AC1. It was AC1 is 753 and it is AC3 is 810. That's okay, but CCD also we immediately conducted, and we found out that again martensite binitic structure and regions will be martensite at very high cooling, and the middle portion we have combinations of martensite binite. Then you will have binite, and then you have ferrite and binite. So this is what we have been observed at this on our that after austenizing and we come at different cooling rate. So all temperatures also given, and we have tableted. Okay, I will go. So next question. So what is that? The first simulation will be our actual heat treatment simulation one. That is what as per the real situations. So we go for austenizing at 9:30 for 10 minutes, and then we are cooling it. First we will be doing that is what 9:30 heating it for austenizing, and then first there will be a cooling will be for cooling, and then while pressing that 15 seconds I will be waiting. Then we are moving from pressing to quenching tank, and then finally I will be quenched to 520 to 60 degree room temperature. So there are once it has been quenched, and then they will be going for a tempering at 660 for 0.5 hour. There will not be any further treatment. There will be subject to property evaluation will be there afterwards. So in case of heat treatment simulation 2, what we done is we do similarly same thing actually. We first one from the furnace 930 to 700, that represents the movement of the hot plate from the furnace to the press hot press. Then from hot press the 15 seconds from 700 to 760 it is taken. Similarly same we have considered. Then finally from hot press 560 to 5, that is what the time it's taken from the press to the hot press to the quenching tank. After then a quenching tank we have been completely room temperature to be moved. All the time will be same you have considered. So the next cycle we introduce extra one, that is will be again a normalizing will be incorporated. Then finally we go for again a 660. So that is what heat treatment simulation 2 actually. In heat treatment simulation 3 we found we put an similarly same, the first part will be same, but what we done is we put in a quenching at, we will be heating at 450 1 hour and then quenching it, then we will go for a 660 actually. So that is what the heat treatment simulation. In case of 4 there will be 450 heating and there are not any quenching, but they are directly go to 660. So that is what all the heat treatment we have to do it with sample in square, or in case of round we can, that is for microstructure study we have to do it. So that is what the temperature plots are given actually for heat treatment simulation 1. That is what normally we do it, and then in case of simulation 2, that's an extra 930 for half an hour. In case of 3, that will be a 450 degree 1 hour in the middle part. Otherwise it did not make any change. But in case of 3, there will be quenching and then we are going it actually. But in case of 4, from 450 directly go to 660 for tempering. So that is what in micro we cannot see able to see such a kind of changes actually. This kind of temper martensite structure, layer structure with carbides are visible, but change according to micro is very difficult. But we found it in dilatometer. There are very small changes are happening. Once once you see it, initially it will go for starting from here, it will goes to the austenizing, it cooling, and there will be a small changes will be there. You are getting a kind of martensite, then you are going for tempering. But once you can see it, this portion while heating, you can see a slight modification changes in across the micron level, very small level. The dilatometer able to predict it. These are representing changes, and they are represents for retained austenite actually. These are all the phases which have been retained. So this kind of high structure which contains a kind of martensite and binary structure tend to have a lot of retained austenite structure. They have the capability to retain them some of the austenite. So the transformation might be completed once it has been coming to the room temperature. So that can typically happen. So these are all changes can happen. So that is what predicted. So in order to avoid this the formation of retained austenite, that is what extra quenching we are 450 are extra quenching, and then going for another heating. So that is why we introduced another in the heat treatment part 3 and 4. Also we are not quenching it but directly going it actually. So then we found out the toughness. But in case of toughness in the simulation 3, you can see there is increase in case of 2 and 1 and 2 are actually actual simulations only. So there are drop will be there, uneven. Some values are not uniform, but there sometimes they get 65, 90 like that is coming. But in case of additional cycle, they are getting 133, 138. But 4 also we are getting 127, 131 like that. So toughness, there are completely the unevenness has been minimized actually. So at the same time you are getting the requirement of hardness also is meeting. So both your toughness and hardness are meeting by this extra introduction of this heat treatment cycle at 450. Either you can quench it or you can also go directly to 660 tempering. So both will tend to reduce the retained austenite formation. Even if it is present retained austenite, you will transform to ferrite and carbide at heating at the middle portion. So that will be helpful to minimize the fresh retained austenite in the micro. So that is what our observation. So after that, our inside manufacturing also they tried many experimentation. After we have proposed them, they are able to solve this problem. So this is one of the main our study in that instrument. Next we will be seeing about another hard cracking studies in Inconel 617 SMAW wells. So hard cracking is one of the problem in these austenitic materials, mostly 617 or 30 for stainless steels. This is defined as a crack that formed during the terminal stage of solidifications. So what you have to do is you have to weld a 617 plate and then use the assembly process and then take specimen accordingly. And the middle where the middle portion weld will be coming and the side where the base material will be coming like that. Then we have to do a kind of we have to do a kind of hot on heating on cooling test actually. So this is a chemical of base material weld metal. There are a lot of differences coming in base metal and weld metal actually. So there are different setups actually. These are the setups that you have to make a separate setup for nil strength temperature. So this nil strength temperature is defined as a temperature while the specimen is heating. We slowly the specimen is heated, but the small load will be given up. 8 kg will be given through the air ram actually. So one temperature automatically will break actually. That breaking temperature we call as an instant temperature. So that is separate setup we been providing, and we have to use it actually. After that, we have to come for conducting on heating and on cooling test. So this on heating, on cooling simply nothing actually is a kind of hot tension test actually. We are on heating means we have to heat the specimen taken from the weld. You have to heat it to 1000 degree or 1100, 1200, 1300, and simply you have to break it actually. So with the one soaking for 1 second and break it at the with threaded sample, we can able to break it at the rate of 50 mm per second. So until fracture, after one bracken, it has been, we have to measure the percentage reduction in area from the changes in the initial and final diameter of the specimen. So in case of on cooling, first we have to heat to the nil strength temperature, which have been conducted determined by this kind of experiment. So this experiment you have to do it initially, and then we have to go for on cooling test. So on cooling test is simply that first you have to go to the nil strength temperature -20. So for example, nil strength temperature may be 1300, -20 is 1280. So first you have to go to 1280, then come to the test temperature of 100 degree or 1100 or 1200 like that. Then you have to soak it for 1 second and then break it similar to the on heating at the rate of 50 mm per second. So we have to do experiments. Nil strength temperature, you can see it actually. We can go faster up to 1200 at the rate of 20 degree faster. But once at 1200, you have to go very slowly at the heating rate of 1 or 2 degree. Very slowly you have to go. At a particular temperature, the material will break actually. Thermocouple also will come out. So at that point, we call as a nil strength temperature. For this case, it is 1312. For weld, for base material, it is 1300. So you made conduct 4 or 5 and break average. So like that, you can found out. So this one, what you have to do is on heating type, different high temperatures, you have to note down the initial diameter, and the final diameter you have to take it, take average from 4 different clock directions, 6 or 12 o'clock, 6 o'clock, or like that. Again, take average of the final diameter, and you have to calculate A0 and AF. As percentage reduction area, calculate A0 minus AF, divide by A0 and 100. So you have to get the value, and you have to plot again another plot with the temperature versus percentage reduction in area. So different temperature axis come in x-axis. So you can see 2 plots will coming on heating. There are a lot of higher value will come, but in on cooling we see lower value, because we are initially we are go to very high temperature, and again we come to the test temperature and we are breaking it. So the reduction area is somewhat lower. And both the curves are plotted, and this BTR we call as a brittleness temperature range. So the brittleness temperature range defined as the difference between the temperature between Nielsen temperature we already found out 1310, and then the lower range will be where you are getting 5% percentage relaxation during the cooling. So this is what BTR. So the BTR range, so more the BTR, the material brittleness will be higher, and the material is prone for hard cracking. When the brittleness temperature range is lower, again your tendency for the hard cracking will be lower. So once the BTR, many researchers are saying that once the BTR range is less than 100, the material is quite safer. More than 150 or 200 or more than 300, like that, your hard cracking tendency are very high. So we can determine this kind of hard cracking tendency for different filler wires or other TIC process, different process also we can able to develop. So these are another samples how we have conducted experiments. So all the cracking mostly will seen at the grain boundary in different temperatures. Only the migrate grain boundary or cracking will along grain boundary granular type. Next we will be seeing, if time is there, can I continue, sir? Or? time is. Excuse me.
Yes, sir. You have 15 minutes, sir. Please continue, sir.
Okay. Thank you. This about TT diagram we call as a time temperature transformation diagram. This is also very helpful for different practical and academic studies. So we are conducted for this kind of a drum boiler material, and what you have to do is we again go first austenize them. First we have the specimens are austenized at 900 degree, so soaked for 5 minutes at the heating rate of 10 degree. So we have to heat it, and once the austenizing are happening, we have to rapidly cool to different isothermal temperature. For example, we have to come from 910, we have to cool to 700. But I have taken 700 at different, not only 700, but up to 350, 700, 650, 600, 550, 500, for like the, I will go with the interval of 50 I have taken. But what you have to keep it isothermally. So what you have to do is you have to once when the temperature 900 cool to 700, make it isothermal. This isothermal, what you have to do is we have to cool very fast actually. As per code, what it says that you have to cool it in the rate of 175 degrees centigrade per second from this austenizing temperature. And what you have to do is you have to generally, if you cool from high temperature, you cannot reach the required temperature. Generally, the undershooting will be there. If you want to 700, it will not reach 700, but it will go to 680, 670 like that. The undershoot will always be there. Again, there will be upshoot also will be there. So all things will be there, but still the code says that you have to maintain within 20 degree. So under this whole temperature should be reached within 2 seconds. So the eternal possible actually gleeble, that is what using this same ISO quench sample is quite possible. Within 2 seconds you have to reach the 700 degree. Even if it undershoot 20 degree is acceptable, and the temperature is you have to maintain, you have to reach it to 700 within 2 seconds. So isothermally 5 plus or minus acceptable. If you want 700, even 705 or 695 also okay as per, and you have to go soak it for whatever our requirements, 2 hours or more than that, like that. So that is what, this is what our experiment go to 910, come to 700, and then I keep it isothermal. So 2 hours and other temperature, 5 temperature I kept at some lower but first 3 experiments conducted for 2 hours. So this is what the plots you can see it actually in the case of 700 actually. So you can see the first plot. Generally that this is what represent temperature, black color, and it comes from 910 to 700, but slightly there will be undershoot will be there, but within 20. And time also you can see it. You can see that 395.5 that given here actually. Within 0.5, within even a very fast time, it able to maintain the 700. So you cannot see that much. It quite easily it meets that requirements. And you can see that this is what the blue color represent dilatometer plot. Again the temperature versus dilation. Temperature dilation versus time also given represent from the blue color. You can see that once it's quenched, there will be the material shrink actually. But once on keeping it isothermal, again that's a transformation. Slowly it's coming actually. It's forming and it is going to the flat portion. That is what represents. We keep it isothermal. The transformation is slowly coming. So at 700, 650, you can see the transformation is slowly moving on. And then at this is 650, this is 600, 550. All we have to do it for whatever the experiments. So all plot together, you can see the dilation versus temperature. From 900 you slowly come, and then this represents isothermal actually, isothermally, and then at different temperatures. Again, this is a dilation, it's a time part, how the transformations are over times. So all the data plotting are very, very useful to find out where what the temperature transformation happening, how the quantity of transformations are happening. In case of this 400, there are Martensite transformations are visible. Other positions you can see a kind of wavy kind of phases there. That will be, you have to check with the microstructure again confirmations. Hardness I will come back afterwards. So this is we have actually what we have done is we have some portions we have magnified actually where the quenching happens. So in case of 700, once the dilation plot is going rising and rising and reaching the flat part, after while it is quenched after 2 hours, there is again a transformation. You can see a kind of a peak. This represents a martensitic phase. So it means that some still it's coming. The portion is not able to meet. Some part of martensite is still coming. It means that some part of austenite was still there in the experiment. Again, in 650, it is conducted for 21 minutes. Again, once it has been starting, and then while it is quenching, it's magnified. There are some small peaks are coming. So once it is 650 for 42 minutes, again that there will not be any phases coming. So in case of confirmation, you have to do some more experiments. So you have to do at shorter duration and also do at longer duration. Make it another confirmation. So like that you have to do it. So finally, what microstructure confirmations we see in that still at 2 hours 700. There are a lot of martensite phases are there, but still binitic and say ferrite and pearlite also there. But dark phases, while quenching it, we found out martensites. So in case of 650, 21 minutes, there are ferrite and pearlite, partly were there. But 42 minutes we are rising it. But some 20 minutes, some you have been actually quenched actually. So after 21 minutes we quenched it. So some rest will be there with the martensitic structure. So in case of 42 minutes, the complete ferrite pearlite. So once 600 degree at 28 seconds, again then we quenched it actually in the intermediate. So it comes from 900, 600, then it quenching. So your structure is been affected. It gets kind of upper binite, and then a lot of structure turns very fine. But once a temperature 600 for long isothermally for 2 hours, you will get a ferrite and pearlite. In 550, we are getting a binite structure. In 556 minutes, again we will getting a kind of binitic type. So in up to 450, 500, 450 on, we are getting a binitic phase. And only at 350, we are getting a martensitic structure. So that is what, but in confirmation, you have to do at small, longer and smaller. And there 450, 13 seconds, you can see it. Some part of phase is there and part of white phase, which has been martensitic, that is not formed because that is not etching actually. So once it has been complete 450, you are getting a complete structure. So that is what it is part, it is not completely transformed. So isothermal complete transformation, you can plot it at based on the temperatures. At 700, we are getting a ferrite pearlitic, and again 650 again ferrite pearlitic, and on 550 range we are getting upper binite, and 450 combinations of martensite and binite, and like that it's coming. So the material can have martensite and binite with ferrite. All things will come at different based on temperatures and isothermal durations. It can form. So next we will be seeing a stress relaxation testing, a kind of a short-term stress relaxation. Generally, creep tests have been conducted to find out metal behavior at high temperatures. But they are being conducted for very long durations. Sometimes more than 2,000 hours, 3,000 hours minimum. There will be some 10,000 hours like that. So any testing which is able to predict high temperature properties, shorter durations are most welcome. So in that case, a kind of accelerated creep testing, a short-term creep testing has been conducted. That's also possible in this instrument. So what we have to do is we have to apply a kind of threaded specimen is taken, but that will be, the middle portion will be having again a shorter diameter. but you have to apply a very small plastic strain of 1 to 2%, 0.1, 0.8 or 2% strain. This is a kind of plastic strain actually, but very slow strain rate, 0.01% you have to do, and the L gauge mode actually, the simulator. And once the applied strain we are raising it at temperature, and then we are allowed to relax. So we have to again plot with the stress versus time and further stress versus strain rate, and again both in the linear scale and log scale. Again, then you can take analyze the data and then take values. So what you have to do is, for initially first you have to whatever the specimen dimension, based on the specimen dimensions, the stress strain curve will change. So you have to any new changes you have to do one stress strain testing actually at whatever the test temperature 550 or 600. We have to use the stainless steel grip is taken because you will get a flat profile, and we can use a very high gripping is there. Clamping, very strong clamping we conducted, and then we have to fit it in the gleeble, and then we have to first you have to do a tensile testing at high temperature to find out what is the level of yield point and yield point, and know what is the level of strain you can employ. After that you have to put a very small strain level, so what to 3 and what to 5 like that total strain. And then within that, the plastic strain both will be coming actually. Plastic part will be there and also elastic part will be there. So actually this is for 550 and 600 we have connected at 2 strain level. For 550 we have connected at 5 strain levels. So after that what we have to do is we have to take the stress versus time actually. So the stress after raising 350 slowly will relax actually. So then what you have to do is you have to make again another plot with the stress is a strain rate. So this slope is taken and we have to take out the kind of n value, exponent value. So it's a kind of a material property, and we can even rank the high temperature behavior. So the next is hard compression testing. This one hard compression, both the kind of we call as uniaxial compression. We very small 15 mm, 10 mm, 12 mm like that we can take it, and then we can weld thermocouples at the middle point on the 2 edge of it, and then this is a separate setup is there for conducting this hard compression testing. So there's an ISO anvil will be there, a tungsten carbide anvil, and we have to raise program, and even there are water quenching jet are there. You can after the simulation is done, once the temperature is compression is conducted, you can just use water quenching jet to freeze the microstructure. That will freeze the grain size. So then you can analyze the microstructures. So that is also available. So with this we can so the thermocouples we can see what is the middle portion, what is the edge portion. You can see slightly, if you mostly you will get a uniform temperature in hard compression because you have used isothermal anvil actually. So we'll get a uniform temperature, and we can after that we can cut it and you can see analyze the, and same time we can see the stress strain plots. So different temperatures we can able to see the at high temperature the flow stress will be lower, but once the temperature is lower we will get a very high stress. So by this we can with the effect of temperature, strain rate, all we better where the material flow is there, where the recrystallization temperature is there. Material tend to where the particular temperature tend to be recrystallized. But this kind of the structure is very high strained in both 1000 and 1050. But 1100 the grains have been forming, new grains are forming. At 1050 also slightly higher, but even 1100 you are able to see better grains. So very fine, but 1200 you can see the change. The grain size is higher. We can the hard compression is one of very important test. Many experiments have been conducted using this instrument. Similarly, heart, we can use a strip specimen and we can conduct a heart tension test. Both, it can be a two strain also, we can conduct a engineering strain. Both we can able to plot. Okay, I think with this I will conclude. Thank you. Thank you, sir. Any doubt?
Thank you, sir. Now the session is open for open discussion. I request the participants to clarify their queries. Sir, let me read out the questions in the chat box, sir. One question by John Rajkumar. How much WRI charges for each experiment, sir?
That I will contact. We have a BRB .B.H.E.L their website. You can see that the consultancy group they are given an email contact or WRConsult.BHL.in. You can contact email. They will provide you offer.
Okay, sir. Thank you, sir. There is no more questions in the chat box. I hope the participants has got almost all the topics crystal clear via presentation. Thank you, sir. Thank you. Thank you so much, sir.
Thank you.
Thanks a lot.
Thank you.
Sir, for the participants, feedback link has been given in the chat box. You can complete the procedure within 1:30 p.m. This is for this session. Attendance will be considered according to the feedback submission. Thank you, sir.
Thank you. Thank you.
Next session will be opens at 2 o'clock. Participants can rejoin at 2 o'clock. Thank you, sir, and thanks to participants also. Thank you so much.
Sam, Satish.
Yes, sir. Sir?
Satish, on the link you can post it in the WhatsApp group also.
Okay, sir. Okay, sir.
Regarding the feedback form, right?
Yes, sir. Yes, sir.
Uh,
We'll post it now, sir.
So I think in the previous morning session and yesterday morning we have posted 4 sessions, right?
Already posted in the chat box, sir. Morning itself.
No, it's the same link you have to post in the WhatsApp group also.
Okay, sir.
Yes, some of them they are asking in the WhatsApp.
Okay, sir. We'll post it now, sir.
Yeah. And who is introduced the today's speaker?
Sir, myself, sir.
Okay, right. Thank you.
Sir? Hello?
Yes.
Sir, I didn't receive yesterday feedback link, sir.
Okay, I will send it 1 second. Don't worry.
Today posted 2 links, sir, but yesterday...
Yeah, yesterday 3 sessions all put together. Morning 1 session, in total 4 sessions. Morning session we will post it.
Okay.
Dr. Rajakumar, sir. Shall we start, sir?
Mani. Satish.
Yes, sir. Yes, sir.
Madam's ready now.
Yes, sir.
Now you introduce today afternoon session speaker. Then you can start the session.
So 1 minute. 1 minute.
Yes, ma'am.
Okay,
yes, ma'am. Take your time.
Screen. ஸ்கிரீன் வந்து தெரியுதா பாருங்க இப்ப.
Yes, ma'am. It's visible, ma'am.
Yes.
Yes, ma'am. Yes, ma'am. Yes, ma'am. Fine, ma'am.
Okay. Camera எங்க காணோம். நம்ம போட்டோ காணோம். இது ப்ளீஸ் பண்ணலாம். நம்ம போட்டோ மாத்திட்டேன்.
Yeah, now it's okay, madam.
Yes, sir.
அந்த பாட்டம்ல ஒரு இது இருக்குல்ல, அதை ஹைட் பண்ணி விட்டுருங்க.
சரி சார்.
ரைட், thank you.
ஓகே.
Satish.
Yes, sir.
You can introduce.
It's a great pleasure to welcome Dr.G.Sasikala ma'am. She is Associate Professor, Department of Information Technology, Annamalai University. She has graduated in B.E. in Electronics and Communication, 1993, Madras University, M.E. in Computer Science and Engineering, 2005, Annamalai University. She has got Ph.D. in Computer Science and Engineering in 2011 in Annamalai University. Thesis title was New Intelligent Solution Algorithms for Engineering Optimization Problems. She is having 21 years of teaching experience and 15 years of research experience. 2 times she has received a Women Researcher Award in 2019 and 21 in recognition of research publications from Annamalai University. She was a co-principal investigator for Tanshare Research Grant project titled Tamil Nadu Electricity Network Analysis with PME placements and IoT for smart grid development. It was worth of 39.85 lakhs during academic year 1920. Her H index is 8 and 259 citations and 29 ME thesis she was guided and 5 research scholars was guided, got the PhD degree under her guidance. And currently 5 research scholars pursuing the PhD degree under her guidance. Total number of papers published was 45. Among that, 15 Web of Science indexed and 26 Scopus indexed journals and 3 UGC indexed. And 13 conferences and presentations was done. And she is a lifetime member in the Institution of Engineers India and lifetime member in Computer Society of India. Let me welcome Dr.G.Sasikala ma'am. I request Dr. Sasikala ma'am to take over the session, ma'am.
Thank you for your nice presentation. Thanks, Rajkumar. Respected ladies and gentlemen, good afternoon to one and all. I am Sasikala, working as an Associate Professor in the Department of Information Technology, Annamalai University. I am here to give a lecture on Swarn Intelligence-based optimization for engineering problems. At the outset, I would like to thank the coordinator, Dr. S. Rajkumar, for having invited me for being a part of this seminar and giving a lecture on this topic. And also, I would like to express my sincere gratitude to Dr. V. Balasubramaniam sir, Professor and Head, Director C Major, for his kind support and encouragement. This is the outline of my lecture. First, I will give the importance of optimization in solving engineering problems, and then I explain a welding problem and how it is mathematically modeled as an optimization problem. Then talk about evolutionary algorithms in general, and then I will explain one of the evolutionary algorithms such as particle swarm optimization. Here it is abbreviated here as PSO, and then I will explain how PSO is applied in solving for the welding problem, and then run the MATLAB based program for solving the welding problem, and finally concludes. Can you all hear my voice?
Yes,
guys? Yes? Okay.
Yes.
Shall we start now?
Yeah.
Okay. Let me talk about what is optimization. So everyone around us is looking for better things in his life. Everyone is demanding for better products these days. Every industry is striving to maximize the profit. So around us, all the products, problems, events, all these require optimization. Even we in our day-to-day life, we inherently solve the optimization problems. For example, if anyone wants to go to anywhere in the world, then he inherently thinks of all the possible routes in different modes of transport, travel, distance, cost, luxury, budget, spacious time to spend, etc., etc. Then he finally chooses the best one depending upon his requirement, and this is a type of optimization problem everyone solves. So all the problems in the world can be modeled as an optimization problems and solved for optimum solution. So the optimization is a magic key that opens the doors of research in all disciplines like electrical, mechanical, civil, manufacturing, chemical, computer science, IT, physics, chemistry, statistics, economics, management, even agriculture, etc., etc. In engineering, all the problems can be modeled as an optimization problem of minimizing the losses or maximizing the efficiency or reducing the weight, etc., etc. So, for example, in mechanical field, the design of a car can be modeled as an optimization problem of different objectives. The objectives can be maximization of output horsepower per a given input fuel, enhancement of fuel consumption by optimal aerodynamic design, minimizing the manufacturing cost, reducing the weight of the car, improvement of the stability of the car while driving, etc., etc. So the optimization is a computational process of either maximizing or minimizing certain objective of a chosen problem, and they are solved through adjusting certain design parameters. Of course, the problem may also have some objective functions and constraint equations. So if you want to solve this problem using computer, then it requires the mathematical modeling of these objective functions and constraint equations. Even in the field of welding, optimization plays a major role in optimizing the welding parameters to improve the quality of the welding. Now let us discuss the procedure for mathematical modeling of such a welding problem as an optimization problem. In aircrafts, different types of aluminum alloys such as AA70756, AA1100 and T6A1 are extensively used, where all these are the combination of the composite materials. So it is difficult to perform welding on such aluminum alloys by conventional fusion welding technique, because the conventional fusion welding can seriously deteriorate the mechanical properties of the joint. So to overcome this issue, another welding technique called friction stir welding has been popularly employed in welding of aluminum alloys, and this technique was developed before 30 years by the Welding Institute in Cambridge, UK, and this is the machine that it performs the friction stir welding. But this welding does not cause melting and recasting of the aluminum alloy material. And it has several advantages over conventional arc weldings, such as better retention of baseline mechanical properties, less distortion, lower residual stresses, and fewer welder defects. The quality of the welding, it can be done by so many performance parameters such as tensile strength, corrosion, etc. Among them, the tensile strength is the most important performance parameter. Larger the tensile strength, better the quality of the welding, and vice versa. So the quality of the welding depends on many parameters. They are tool rotational speed represented by N, and welding speed denoted by S, axial force F, shoulder diameter capital D, pin diameter small d, and then the tool material hardness represented by H. So any change in these parameters will have a significant influence on the quality of the welding. In other words, what we can say that the desired quality of the welding, it can be obtained by tuning these parameters. So the problem is how to obtain the optimal parameter values to obtain the best performances. For example, obtain the optimal parameter values that maximize the tensile strength here. So now the problem, it can be formulated into an optimization problem of the objective here is maximizing the tensile strength while treating the 6 parameters such as tool rotational speed, and then the welding speed, axial force, shoulder diameter, pin diameter, and the tool material hardness. All these are considered as unknown variables. So now this is the objective function of the welding optimization problem. Here now the problem here is the function psi relating to the 6 problem variables based on 6 parameters with the tensile strength is not available. As the welding machine is a non-conventional complex machine involving so much of electronics, integrated circuits, and microprocessor based control systems. So here the objective here is the maximization of the welding optimization problem. Here the TS, which is related to the all the control variable. But if the function is provided by the manufacturer of the welding machine, then this type of optimization problem, it can be easily solved. But such function is not usually provided by the manufacturer. So a simple possibility is to develop some empirical equations by experimentally measuring the tensile strength for samples welded with different parameter values. So in this regard, we have to perform 500 or 1000 sample welding by varying these parameters randomly and experimentally measuring the tensile strength. For example, we have to experimentally obtain the data set. So here this example data set, it contains 25 data values where each data set is obtained by setting these 6 parameters and experimentally for welding 2 pieces of aluminum alloy and then experimentally measuring the tensile strength, which is the target value given in the last column of this table here. So now this table requires welding of 25 samples of aluminum alloy. So once we obtain the data set, next we have to model the data here. So it can be done by regression methods such as linear regression, multiple linear regression, or non-linear regression, or any other polynomial equations. Even artificial neural networks can be applied for developing the mathematical model. The accuracy of the model, it increases the number of tested data sets. Larger the data set, greater will be the accuracy and vice versa. So now we see in this table, here the 6 variables based on 6 parameters, they are lying at different ranges. For example, the first variable, which is based on the tool rotational speed represented by n, where it is in terms of around 1000 here, 1000 value. Whereas the 5th variable, that is the pin diameter, which is less than 9 here. So while modeling, all these values are usually normalized in the range of -1 to 1 or 0 to 1 or any other suitable range. So this is done for bringing all the parameter values in a uniform range. So once we model the data, next we have to develop the mathematical model or develop the functional equation for estimating the objective function of the optimization problem. Here the objective function is maximizing the tensile strength. So we have to obtain the developed equation for estimating the tensile strength here. So in this regard, so here the coordinator of the FDP, Dr. S. Rajkumar, he has published a paper on mathematically modeling the welding machine. So here the title of the paper is given in this slide. So if you find any free time, you can refer that paper. So in that paper, he experimentally obtained the data set for 52 welded samples. And then he developed the regression function equation for estimating the tensile strength here. While modeling, he normalized all the data in the range of -2.378 to +2.378. And this is the developed regression function equation, where this developed function with the tensile strength with this 6 control variable is given here. So now we developed the equation for estimating the objective function of the welding optimization problem here. So now the problem, simple welding problem, it can be formulated into an welding optimization problem of objective here is maximizing the tensile strength, which is represented by the developed equations already given in the paper. So I consider that I developed a model for estimating the tensile strength and subject to the constraint equations of the lower and the upper limits of the problem variables, such as minus 2.378 to plus 2.378. Now we formulated the problem. Okay, and once the problem is developed, once the problem is modeled into an optimization problem, then this type of problem, it can be solved by using any optimization technique here. So here I have chosen the PS4 algorithm to solve this welding problem. So we are going to solve this welding problem using particle swarm optimization. So once the optimal values are obtained, then these values are encoded from the normalized range of minus 2.378 to plus 2.378 to the actual range of 800 to 1000 for the first variable and so on. Okay. So now let us, before going to see the solution process of this welding problem, now let me know about what is the general format of the optimization problem and what is local maxima and what is global maxima and what is optimization algorithm. How do we obtain the global maxima using conventional optimization approaches, and what are the drawbacks in the traditional approaches, how they are overcome by the evolutionary algorithms, how do we obtain the global maxima in evolutionary algorithms. Let us see them one by one here. So now the formulation of these optimization problems could differ from problem to problem. So these problems may involve linear terms or non-linear terms or a combination of both for objective functions and the constraint equations. The general format of the optimization problem will contain at least one objective function with one or more constraint equations. Now this is the general format of the optimization problem. Here the objective function here is either maximization or minimization, which is represented by pi equal to f of x, and subject to the constraints of g of x equal to 0 and h of x less than or equal to b, where the input variable or the problem variable, which lies in between x minimum to x maximum here. So in this general format, we have four equations here. So in this four equations, the first equation, it represents the objective function of the optimization problem. Okay, and whereas the fourth equation, it represents the minimum or maximum values or the lower and upper limits of the problem variable that we used in the function equation here. So in addition to this constraint equation, there are two more equations are there. That is, the g of x is called as the equality constraint and h of x is the inequality constraint here. But in our, now we have the question, ma'am, in our welding problem, we are having only two equations. Yes, of course, we are having only two equations. The problem has two equations. One is the objective function, that is maximizing the tensile strength. And the other one is the constraint equation defined by the limits of the problem variable here. So, but in general, the optimization problem may also have some equality constraint g of x and inequality constraint h of x here. But in our welding problem, there are no such explicit constraints here. So based on the objective function and the constraint, one of the constraint equations, we formulated the simple welding problem into a welding optimization problem. So that's why I said earlier, the formulation of these optimization problems could differ from problem to problem. So next is we should see about what is evolution, what is optimization algorithm. An optimization algorithm is a procedure which is executed iteratively by comparing various solutions till the optimum or the satisfactory solution is found. Various algorithms such as integer programming, dynamic programming, nonlinear programming, all these are extensively used in solving the optimization problems, where the emphasis is on maximizing or minimizing certain objective. So unfortunately, a single optimization algorithm which will work equally efficient on all optimization problems is not available in the literature. So some algorithms perform better on one problem, but poorly on the other problems. So that's why a large number of algorithms, each suitable to a particular type of problem, have been suggested in the literature. However, these algorithms do need a good starting solution for obtaining the optimum solution. Otherwise, they may land at a local minimum or local maximum, which is away from the global solution. So this is considered as the main drawback of the conventional optimization approaches. So to overcome this issue, recently evolutionary algorithms have been suggested. So evolutionary algorithms such as genetic algorithm, simulated annealing, evolutionary programming, particle swarm optimization, honeybee optimization, ant colony optimization, chemical reaction based optimization, firefly optimization, dragonfly optimization, teaching learning based optimization, cuckoo search algorithm, flower pollination based optimization, football player game optimization. All these algorithms are extensively used in solving the optimization problems, where these methods have the ability to search the whole solution space to find the global best. And these methods use random choice is a tool based on a well-directed search mechanism, and they do not need the derivatives of the objective functions in the constraint equations. And furthermore, these methods succeed to optimize the multimodal, discontinuous, and time-varying functions. The main drawback of these methods is that they need large computational time, and they may not be suitable for real-time applications. And however, these algorithms are said to be robust because there is no restrictions on the solution space are made during the search process here. So now let me know about what is the global maxima and local maxima. Let us consider this diagram. So in this figure, there is a plot between the objective function values versus the solution point x. So here the x-axis, it represents the solution points, and the y-axis, it represents the objective function values. The space between x and y-axis, we called it as the solution space, problem space, or the search space here. So here, each point in the x-axis, it represents a values of the set of values of the decision variables or problem variables. For example, if a problem has 3 variables, say x1, x2, x3, then each point x in the x-axis, it represents a set of values of the decision variables x1, x2, x3. X is not a single value. Just keep it in mind. That is, here each, that is, x is a combination of 3 variable values of the 3 variables x1, x2, x3, what we have chosen in the problem here. So similarly, the y-axis, it represents the objective function values. Now let us assume that the problem has multiple peaks in the search space here, where these peaks are called local maxima, and the top one is the global maxima here. So here the objective is to find the solution corresponding to the global maxima. While solving this problem using conventional optimization algorithms, we have to give initial starting values of x. So if the starting values of x are nearer to the local maxima, then the algorithm adjusts this initial solution point in such a way to reach the suboptimal solution, which is not a optimum one here. So if the starting values of all the values of x are nearer to the global maxima, then the algorithm settles at this point and give this as the global solution here. So therefore, the solution given by the traditional algorithms depend upon the initial values of the starting values of x. If a problem has a minimum number of variables, say for example, if we are having only 2 or 3 variables, then we can easily visualize the search space in a 3-dimensional plot, and we can easily give a starting solution nearer to the global maxima for obtaining the optimum solution. But if the problem has more number of variables, say for example, if it is 10, 20, 50 or 100, then in such case we cannot imagine the solution space, and we cannot easily give the good starting solution to the global maxima for obtaining the optimum solution. So for a larger problem with a large number of variables, as we do not know where exactly the local maxima exist and the global maxima exist, so in such case we have to repeatedly run the conventional algorithms with different initial starting values of x and choose the best one as the optimum solution. But there is no guarantee that the obtained solution is the global one. Maybe there are chances that we get better solution with another starting solution. So in this, so far what we have discussed about the optimization. So by this time, you might have known a brief of about the optimization. What is local maxima? What is global maxima? And what is the definition of the optimization algorithm here? Okay. So in this lecture, my aim is just to outline the procedure for using the evolutionary algorithms in solving this type of optimization problems here. So among the evolutionary there are many evolutionary algorithms available in the literature. Among the evolutionary algorithms, what I have chosen here is the particle swarm optimization. Why I consider the PSO for solving this 6-variable welding optimization problem means because it is simple. Simple in the sense, given the basic form of the algorithm yields best results, and the program can be developed by anyone in short duration, and it can be used by anyone with an understanding of the problem at hand without needing any extensive background in the optimization theory. Now let us see that what are all the general procedures available in solving this type of optimization problem using evolutionary algorithms. So let us now recall the same welding optimization problem what we discussed at the beginning in the previous slide. So here now this is the objective function of the welding problem, that is maximizing the tensile strength subject to the constraints of the lower and upper limits of the 6 problem variable based on 6 parameters. So now the problem here is to obtain the optimal parameter values of this variable that maximize the tensile strength here. So here, while solving this type of optimization problem using evolutionary algorithm, the first step is we have to identify the problem variables and classifying them into control variables, dependent variable, and independent variables. So in our welding problem, there are 6 variables based on 6 parameters. But these 6 variables are considered as the represented as the control variables or the decision variables. So these control variables such as N, S, F, B, D, and H are to be optimized to obtain the objective of the optimization problem, that is maximizing the objective, maximizing the tensile strength here. So the tensile strength is considered as the dependent variable as it depends on the value of the 6 control variables here. And then the specifications such as the lower and the upper limits of the 6 problem variables are considered as the independent variables. The independent variables are given as the input data to the problem. So now we have identified the problem variables and classifying them into control variables, dependent variables, and independent variables. Now the control variables are the 6 variables in the welding problem based on 6 parameters, and then the dependent variable is nothing but the objective function of the optimization problem, that is the tensile strength, and then the independent variables are nothing but that is the lower and upper limits of the 6 control variable, that is minus 2.378 to plus 2.378 as the independent variable. Okay, and then after that we have to form the next step is we have to form the fitness function or cost function. So in general, the objective function of any optimization problem can be either a minimization function or maximization function. So if the chosen objective function of the optimization problem is loss means, then the objective function will be formed as a minimization function. So here it is represented as minimize psi equal to loss of x here. But if the chosen objective is profit, then the objective function will be a maximization function. It is written as maximize pi equal to profit of x here. So similarly, the optimization algorithms are developed to handle either a minimization function or maximization function. For example, the algorithms like genetic algorithm, honeybee optimization, biogeography based optimization, and the flower pollination based optimization, all these algorithms are formed to solve the maximization function. Such maximization function is often referred to as the fitness function in evolutionary terminology here. So why it is referred to as the fitness function means, so in human psychology, fitness always be maximized. That is efficiency, we need always be maximum efficiency here. So if the objective function of any optimization problem is maximization function, then that maximization function in terms of evolutionary terminology, we called it as the fitness function here. Okay, so if now there are few other algorithms such as simulated annealing and then ant colony optimization, all these algorithms are formed to solve the minimization function. There's such a minimization function in evolutionary terminology, it is referred to as the cost function. That is, in human nature, we always reducing the cost. We need to minimize the cost here. So if the objective function of any optimization problem is minimization function, in evolutionary terminology, it is called as the cost function here. But the PSO can handle, that is, in all the evolutionary algorithms, some algorithms perform better on the maximization function, some algorithms perform better on the minimization function here. But the particle swarm optimization, that is the PSO, it can handle both the maximization function and the minimization function. That is both the fitness function and the cost function here. So in our welding problem, as our objective is maximizing the tensile strength, so the maximization objective, it can be directly considered as the fitness function here. So that's why here I written it as maximize fitness pi equal to the tensile strength here. Tensile strength for the welding problem here. So if you want to represent the same welding problem other than the particle swarm optimization such as a simulated annealing, then we need the cost function here. So in such case, the maximization, it should be directly transformed to the minimization function to form the cost function here. So here the minimized cost is I equal to 1 by 1 plus TS here. So that is the minimization of the cost that will maximize the tensile strength. That is, if the objective function of any optimization problem provides the optimum solution of minimizing the cost, means the solution that will maximize the tensile strength here. So once the problem variables are identified and form the fitness function or the cost function, then this type of problem, it can be solved by using any one of the evolutionary algorithms such as GAS, PSO, etc. here. Where all these evolutionary algorithms, they uses a population and a solution iterative process. That is, in this case, in this welding problem, I considered the PSO. So in PSO, either fitness function can be used or the cost function can be used here. But in our lecture, as our objective is maximizing the tensile strength, I would like to choose the fitness function for solving the welding optimization problem here. So before going to solve the problem using PSO, let me all know about what is particle swarm optimization. Let me brief it now. So here, the particle swarm optimization is used to find an optimal solution of any optimization problem. It belongs to the class of direct search methods, usually derivative free, meaning that they depend only on the evaluation of the objective function. It was first described by James Kennedy and Russell Abbott in the year 1995, and this is a population-based stochastic optimization technique modeled on swarm intelligence. So swarm intelligence, often referred as the collective intelligence, which is based on social psychological principle, which provides insights into social behavior as well as contributing to engineering applications. Social influence and social learning enable a person to maintain a cognitive consistency. That is, people solve problems talking with other people, their beliefs, attitudes, and behaviors. And this could be depicted as the individuals moving towards one another in a socio-cognitive space. So PSO simulates such kind of social optimization. And PSO combines a social-only model and a cognition-only model. And social-only component suggests that individuals ignore their own experience and adjust their behavior according to the successful beliefs of individuals in the neighborhood. So in this particle swarm optimization, a population of individuals called particles are initialized with random guesses in the search phase here. So each particle, it represents a candidate solution to the problem at hand, and these particles fly around in a multi-dimensional search space with a velocity V of t. So often we are going to discuss some of the terms based on this PSO approach, and they are represented as, first one is the particle. Here the particle which is represented by the letter X here. So here it is mentioned as Xj of t. Xj of t means it is a candidate solution of the jth particle represented by m dimensional vector, where m is the number of control variables. And then the second one is the population, that is pop of t. It is a set of n particles at instant t here. Where this population, it is represented by m dimensional vector, where that m dimensional vector, it is in the form of a matrix equation which is given here. Okay. And then the third one is the particle velocity. V of t, it is the velocity of the moving particles. Again, it is represented by a m dimensional vector. It is in the form of a matrix equation given in the slide here. So these particles communicate good positions to each other and adjust their own positions and velocity based on these good positions. So two best values are to be considered at each iteration. So one is the particle best and the second one is the global best here. So particle best, or otherwise we called it as the local best also. So here the particle best is represented by x star of t. It is the best position that each particle has achieved so far at instant t, where it resembles the autobiographical memory as each particle remembers its own experience. And then again it is represented by the m dimensional vector, which is given in the form of a matrix equation shown in the slide here. And the second one is the global best x. It is denoted by x double star of t. That is, it is the best position among all individual best positions of the particle. That is, the swarm has seen so far. So, which is similar to publicized knowledge. Again, it is represented by the equation which is given here. So, to understand well about this local based and the global based, to know about about that local based and the global based, let us consider this figure. So, in this figure, there are two particles, one with the green color and the other with the red color here, where these two particles fly and occupy new positions from instant to instant here, where this black colored arrow mark indicates the direction of the movement of the particles. That is, the x-axis, it represents the time instant, and the y-axis, it represents the fitness values here. So initially, the fitness values of these two particles are set as 200 for green particle and 400 for red particle. So at this 0th instant, these two fitness values are considered as the local best values of these two particles. So among them, the global best is 400 here. Are you having any doubt? Do you have any doubt to find the global best? So here 400 and 200 are the local best of the two particles. Among them, the 400 is the global best. So when these particles fly and occupy the new position at the instant 1, when the fitness values are updated here. That is, for the green particle, the fitness value is updated from 200 to 250, whereas for the red particle, the fitness value is reduced from 400 to 350 here. So now the fitness values of these two particles are set as 250 for green and 350 for red at instant 1 here. So from this fitness value, again we have to find the local best values of these two particles here. So for that, we have to compare the fitness value of the current instant to the fitness value of the previous instant here. So at the instant 1, for this green particle, the current fitness value is 250, which is greater than the fitness value of the previous instant 0 here. So this 250 is considered as the best fitness, and it is considered as the local best value for the green particle at instant 1 here. So similarly for the red particle, here the 350 is lower than the previous fitness value. So here the previous fitness value is considered as the best fitness, and it is remained as the local best value for the red particle at this instant here. So now at instant 1, the local best values of these two particles are set as 250 for green particle and 400 for red particle here. So among them, the global best becomes 400, which remain unaltered. Okay, so now at the instant 2, again the fitness values are updated from 250 to 300 and 350 to 450. Among them, 450 becomes the global best here. So finally, at the instant 5, the global best becomes 500 here. So in this way, the global best, particle best, and the fitness values are updated. Do you have any doubt in that? To find the local best and the global best? Okay. So after finding the two best values, then the particles will change their positions and velocity accordingly, so that new information is broadcast to the swarm here. So the velocity and the particle positions are updated by using these two equations. The first one is the velocity updation equation. So in this velocity updation equation, the second term is the cognition component, and the third term represents the social component here. So in this velocity updation equation, where this x of t minus 1 is the current particle position, and the x star of t minus 1 is the local best value, and the x double star of t minus 1 is the global best value here. So in addition to this local best and the global best value, there are some constants are also present, where C1 and C2 are positive constants, R1 and R2 are random numbers in the range of 0 to 1, and W of t is the inertia constant. Actually, this inertia constant, it acts as the control parameter, which is used to control the impact of the previous velocities on the current velocities. So hence it influences the trade-off between the global and local exploration abilities of the particle. For initial stages of the search process, large inertia weight to enhance the global exploration is recommended, while for last stages, the inertia weight is reduced for better local exploration. So here, the inertia weight is altered by using the third equations, such as it is given as W of t equal to alpha into W of t minus 1, where this alpha is a decrement constant. Usually the constant value is small, but it is closer to 1 here. So after substituting all these values and computing the new velocity value here, so this new velocity value is substituted in the particle position updation equation, now which is given by the second
Sorry to interfere.
Yes?
I'm having a question to you. Shall I
Yeah,
ask?
at the end of the lecture.
Okay,
Or
fine.
at this time.
What
At the
time?
end of the lecture.
No,
At
no,
the end
hold
of
on.
the lecture.
Okay.
Yeah.
Anish,
Do you want now?
no, you can ask in the end of the session. Madam, you can
Yeah.
continue.
Yeah, okay. So after computing this new velocity value, then this new velocity is substituted in particle position updation equation, and then the new particle position values are calculated here. So in this particle position equation, V of t is the velocity value what we obtained from the previous equation, and this x of t minus 1 is the current particle position, and x of t is the new particle position here. So in this PSO approach, what we have seen about some of the terms such as the particle velocity, population, and then the particle, and then velocity updation equation, particle position updation equation, so far what all we have discussed about. So based on this concept of this PSO approach, the algorithm as follows. So in this algorithm, first we have to choose the suitable values for PSO parameters, and then set the time counter, that is the iteration counter t equal to 0, that is initial of the iterative process, and then initialize the population, generate randomly n particles and velocities for all particles within their respective range, and then evaluate the objective function for each particle, and store all the particles as particle based as x star of 0 and pi star of 0, and search for the global best x double star of 0 and pi double star of 0 and store them, and then update the time counter using this equation t equal to t plus 1, and update the inertia weight w of t equal to alpha into w of t minus 1, then update the particle velocity v of t using this equation, then check for the velocity limit, again update the particle position, then update the particle position limits, then evaluate the objective function of each particle, and then update the particle based X star of T, global based X double star of T, and check for convergence. Here the convergence is based on two criteria. So if it is converged means then the global based at the specific number of iterations will be considered as the optimum solutions within the results in stop the algorithm. So if it is not converged means we have to go to step 4, that is again we have to increment the iteration counter, alter the inertia weight, update the particle position, update the velocity equation, and once again calculate the objective function equation or fitness value, and once again update the local based and global based, and this procedure should be repeated for the specific number of iterations what we have chosen in the algorithm. So you might have understood now what is the algorithm based on this PSO approach. Yes? It's no answer at all.
Yes, madam. Yes, madam. We understood. We have followed. Thank you, madam. Thank
you. Okay. So now, based on this PSO algorithm, now I would like to discuss the step-by-step procedure for solving the welding optimization problem using PSO, so that you all may understand how this algorithm works in a better way. Okay. So now let us recall the same welding problem what we seen just before in the slide. So here the objective function of the welding optimization problem is maximizing the tensile strength, which is represented by the developed regression function equations, which is already given in the paper. So I took that equation already. Okay. And then subject to the constraints of minus 2.3782 plus 2.378 for all the 6 problem variables here. So here the problem is to obtain the optimal parameter values of these 6 variables that maximize the tensile strength. So as we discussed earlier, first we have to represent the problem according to the PSO format, and then the solution process to be carried out after choosing the PSO parameters. Okay, so here the first step is we have to define the particles and their range. So here in this in PSO approach, the problem variables or the decision variables or the control variables are represented as particle here. So in our welding problem, each particle is represented by means of a 6 variable based on 6 parameters. So here in each particle it can be represented by a 6 variable vector, that is N, S, F, D, D and H, which is given as the first equation here. That is X represents the particle. So here each particle is represented by a 6 variable based on 6 parameters in this welding problem. Okay, so here we define the particle by means of a 6 variable vector, which is the first equation given in this slide here. And after that, we have to define the range for each variable of the particle here. So already we normalize the range for each variable is minus 2.3782 plus 2.378 here. So here the range for each variable is minus 2.378 to plus 2.378. These two are considered as defined as the constraint equations which are given by the second and the third equation. That is x minimum equal to minus 2.378 for all the 6 variables, and then x max is plus 2.378 for all the 6 variables. Okay, so now there is no doubt at all. So now we define the particles and their range. The range is also we normalized at the beginning of the problem, that is minus 2.378 to plus 2.378 here. And the next step is we have to define the fitness function. So in our welding problem, the objective function given here is strictly we considered as the fitness function here. So here the fitness function is defined by means of 6 control variables, which is based on the developed regression function equation, which is given here. Okay, so now we define the particles and formed the fitness function also. Next step is we have to select the PSO parameters. So in PSO, certain parameters such as the constants C1 and C2 and the random constants R1 and R2 and the inertia constant W of T, and then the decrement constant alpha, population size, and the maximum number of iterations for convergence check are to be selected here. So now let us choose for this welding problem the constant values of such as C1, C2 as 2, and then the inertia constant W of T as 1, and then the decrement constant alpha as 0.98, and the population size as 6, and the maximum number of iterations for convergence check are 100 here. So after selecting this PSO parameters, and the fourth step is we have to fix the range for the velocity limits. Now you have the question, ma'am, why we have to fix the range for the velocity limit? Okay, let me explain that one. Why? What is the importance of fixing the range for the velocity limits here? So in PSO, the new particle position is obtained by adding the new velocity value with the old particle position. So if the calculated velocity value is very large, then the new particle position will jump from one corner to the another extreme corner of the search space, which is undesirable. So let us consider this figure. So in this plot, I consider only the first two variable of the particle. But in our welding problem, we are having 6 variables to define the particle here. So why I am not considering the 6 variable means it is tedious to plot a 6 variable mesh in this search space to explain the velocity limits. So that's why I consider only the first 2 variable of the particle. It is easy to plot to explain the velocity limit in this search space here. So now let us assume that the problem has only 2 variable, and this is a search space for the 2 variable problem. Here in this search space there are 2 spots, one with the black color and the another with the red color here. And then the blue color arrow mark, it indicates the direction of the movement of the particles here. So there are in our welding problem here the population size, that is the population size as 6. We have chosen the population size as 6. So 6 particles we are considered. So here the black spots it represents the initial positions of the 6 particles, that is 1, 2, 3, 4, 5, 6. So there are 6 particles in their search space here. So the black spots, it represents the initial position of the particles. These particles move to the new position by adding the new velocity value which are written in the bracket here. Now the red spot, it represents the new position of the particles here. So among the 6 particles in this search space, one particle jumps from one corner to the another extreme corner of the search space here. So if all the particles jumps like this, then the algorithm will not converge. That is, it will not settle to an optimum solution. So therefore, the movement of the particle at each iteration, it should be restricted or limited here. Here the movement of the particle, it depends upon the velocity value. So the velocity value of each particle, it should be limited or restricted at each iteration here. So in order to limit the velocity values, the equation is fixed to calculate the velocity limit. Here Vmax equal to x max minus x minimum divided by capital N here, where x is nothing but the particle and x minimum and x maximum are the minimum and maximum values of the problem variable x here. And then this k, it represents the number of variables for each particle here. And then we have to choose the value for n, and depending upon the problem by trial and error method. Usually the range of n, it can be the value of n, it can be in the range of 10 to 25. So in our welding problem, the minimum and maximum values of these variables are set as minus 2.3782 plus 2.378. So now substitute these values in this position and let us choose 10 for n for this welding problem here. So after substituting all these values, then the velocity value, it can be calculated as plus or minus 0.4756 here. So now we fix the range also. So next, let me see that how the solution process to be carried out. So now we have identified the problem variables, formed the fitness function, selected various PSO parameters, and then fix the range for the velocity limits also. So the next step is we have to generate the initial population. So here in this case, in this PSO, each particle is defined to represent the 6 variables here. That is N, S, F, D and H here. So we have to generate the value of the variables within the range of minus 2.378 to plus 2.378 called initial population. So here the population size is 6. So we have to generate 6 sets of values of the particles here. So here the 6 sets of values within the range of minus 2.378 to plus 2.378 are generated, and they are called as the initial population, which is shown in this first tabulation here. So similarly, we have to set the velocity values of all these variables for each particle as 0, and it is shown in the second tabulation here. That is all the velocity values for the particles set as 0 here. Okay. So now in this population, now each particle, it contains the values of the variables such as N, S, F, D and H here. Now substitute all these values in the fitness function equation and calculate the fitness value. That is, already we developed that regression function equation for estimating the tensile strength. That is the objective function of our welding problem here. So that is based on the control variables. The developed function is developed here. So now substitute all the values of the variables in that fitness function regression equation and calculate the fitness value here. So this is repeated for all the 6 particles, and all the fitness values of 6 particles are calculated, and they are given in the next column of this table, which is represented as pi of 1 here. That is, pi represents the fitness and 1 represents the iteration number 1. That is at the beginning of the iterative process here. So after obtaining the fitness value, that is after calculating the fitness value, next we have to find the local best values for all the particles here. So to find the local best value, we have to compare the fitness values of the previous iteration for all these particles here. So initially at this stage, so we have to set the previous iteration, that is the 0th iteration. The fitness value of the 0th iteration for all these particles are 0 value, and they are given in the last column of this table, which is represented as pi star of 0 here. That is, there is a difference between pi and pi star here. That is, pi represents simple fitness value, where this pi star represents the local best value based on the fitness value of the particles here. So now we have the fitness value of the current iteration and the previous iteration here. So from these values, now compare the fitness value and consider which one is the best, is the local best here. So here for this, in this table, let us consider for the first particle. Here for the first particle, the fitness value is 349.71, whereas the previous fitness value is 0 here. So here comparing these two fitness value, here the 349.71 is the better value here. So for this first particle, the fitness value, that is the available fitness value of 349.71 is considered as the local best value for the first particle, and this is repeated for all the 6 particles here. So at this stage, at this first iteration, the current particle and then the available fitness values are considered as the local best values of all the particles, and they are given in this tabulation represented as a pi star of 1, and the corresponding particle values are considered as the local best particle positions represented as x star of 1 in this tabulation here. So once we obtain the local best values of the particles, that is, local best means what? It is nothing but the identification of the best value that each particle has achieved so far here. So once obtained the local best values of all the particles, next we have to find the global best value here. So in this table, that is the global best means the particle with the largest fitness is considered as the global best here. That is the so and the corresponding particle values are considered as the global best particle positions. So at this iteration number 1, in this table, the particle 2 is the best one here, as its fitness value is 357.29, which is considered as the largest fitness, which is larger than the fitness of the remaining particle. So it is considered as the global best and represented as pi double star of 1, and the corresponding particle values are considered as the global best particle positions represented as x double star of 1 here. Okay, so here after finding the local best and the global best value, then we have to increment the iteration counter using this equation t equal to t plus 1, and then alter the inertia weight w of t equal to w of t minus 1 into alpha. That is alpha what we have chosen in the algorithm is 0.9. Usually it may be in the value of 0.95 to 0.98. So what I consider here is only 0.98 here. So after altering the inertia weight using this local best and the global best value, then update the velocity and the particle position of each particle in the population here. So here the velocity, now let us see how to update the velocity values here. So here the velocity equation is given, the explanation of the velocity equation already we have seen before in the slide here. Okay, so in this velocity equation, where this x of t minus 1 is the current particle position, and x star of t minus 1 is the local best value, and x double star of t minus 1 is the global best value, where all these values are what we obtained from the previous iteration. Here, okay, in addition to these values, there are constants, some constants also present here. So let us choose the value what already we have chosen, the constant value of C1, C2 as 2, and R1, R2 in the range of 0 to 1, and W of t as 1 here. So now substitute all these values in this velocity updation equation and calculate the new velocity value here. So here, this in our welding problem, each particle is represented by 6 variables here. So we have to generate 6 sets of values of the variables for each particle based on this velocity updation equation here. So now the velocity values of all the particles are calculated and they are given in this velocity tabulation here. So after calculating the velocity value, again we have to check for the velocity limit here. So if the velocity value exceeds the limit, then it should be replaced by the respective limit here. So already we calculated the velocity limit value as 0.47 plus or minus 0.4756 for this welding problem here. So here in this table, all the yellow shaded box, it contains the violated velocity values here, whereas the other values are within the range, that is they do not exceed the limit of 0.4756 here. So the yellow box, it must be replaced by the respective limit of 0.4756 with its appropriate plus or minus signs here. So here the second table, now it shows the new velocity value after imposing the velocity limit of 0.4756 here. So here in this table, let us see, for example, here the variable is for the obtained velocity value by the equation is 1.25 here, where this calculated velocity value which exceeds the limit of 0.4756. So here it should be replaced with the respective limit of 0.4756, where its magnitude is here positive, again its magnitude is here positive here. So this is this is similar to other remaining particles which is shaded by yellow color here. So now using this new velocity value, then update the new particle position here. So the newly available velocity values are updated used in the particle position updation equation to find the new particle position here. So the new particle positions are updated and they are given in these 6 columns here. So now at this iteration 2, now each particle contains the new particle position values of all the 6 variables here. Okay, so now substitute these new particle values in the fitness function equation and once again calculate the fitness value here. So here this should be repeated, this should be done for all the 6 particles and the fitness values are calculated for all the 6 particles and they are given in the next column of this table, which is represented as pi of 2 here. That is 2 represents the iteration number 2 here. Okay, so here after obtaining the fitness value, then we have to update the local best value here. So how to update the local best value? We have to compare the fitness value with the current iteration to the previous iteration here. So already we done the local best values. Already we obtained the local best values of the previous iteration, which is represented as pi star of 1, is given in this last column of this table here. So now we have to compare the fitness value of the current iteration 2 and the local best values of the previous iteration pi star of 1 here. So in this table, for the first and the second particle, the fitness values of current iteration is lower than that of the fitness value of the previous iteration here. So here the previous local best value is considered as the local best value of these two particles for the present iteration. For the current iteration, that is for iteration number 2 here. Whereas for the remaining particles, the fitness values of iteration number 2 is greater than the fitness values of the previous iteration here. So here the fitness value for the remaining 4 particles is the local best values for this iteration 2 here. So now the newly available local best values are given in this column of this table, that is represented as pi star of 2, and the corresponding particle positions are represented as x star of 2. So once we find the local best values, then again we have to update the global best here. So the global best procedure is what? Well, the particle with the largest fitness is considered as the global best here. So at this iteration number 2, in this table, the particle 3 is the best one. The fitness value is very large compared to other fitness values of the particle. So it is considered as the global best 362.47 as the global best represented as pi double star of 2, and the corresponding particle values are considered as global best particle positions represented as x double star of 2 here. Okay, so now we updated the local best and the global best values here. So after updating the local best and the global best, then we have to increment the iteration counter. So before proceeding for the iteration, we have to check for convergence. So here the convergence is based on the number of iterations here. So here the number of iterations reaches the maximum number of iterations, then the algorithm is converged. So for this welding problem, what we have chosen, the maximum number of iterations for convergence check is 100 here. So but here the current iteration is 2. So 2 is less than 100, so it is not converged here. So whenever the iteration T reaches the maximum value of 100, then the global best is considered as the optimum solution to print the results and stop the algorithm. But at this stage, the iteration is not converged here. So we have to continue the process. So again, by incrementing the iteration counter and alter the inertia weight by using this equation, again update the particle velocity and update the particle position, and then after finding the local best, and then update the global best, and once again calculate the fitness value. And this procedure should be repeated for 100 times here. That is the specified number of iterations what we have chosen in this algorithm. So in this welding problem, what we have chosen is 100 here. So this is the table, it shows the state after the 100th iterations. So here, after 100th iterations, in this table, particle 3 is the best one, as its fitness value is 374.89, and it is considered as the global best value, and the corresponding particle values are considered as the global best particle positions of these variables of the particle here. But actually, these values are values are in the form of a normalized range here, but the optimum solution, it needs the values in the actual range here. So here the optimum solution in the decoded actual values are given in the last row of this table, and the corresponding fitness is 374.89 after the 100th iterations here. So if the welding is performed with these parameter settings, then the welded piece will have a tensile strength of 374.89 here. That is, what is the parameter settings? That is a decoded actual range, means N value is 1429.4, and then the rotational speed is 67, axial force is 8.2, and then the shoulder diameter is 15.6, and pin diameter is 5.1, and then the tool material hardness is 596.5 here. Okay, so far what we have discussed about the evolutionary algorithms, and then one of the evolutionary algorithms such as particle swarm optimization, how this PSO is applied in solving the building problem here. Okay, so next we shall see about the coding of this problem here. I have developed the MATLAB coding for this welding problem, and let me show you how it is working on in green. How do we obtain the global best when running the algorithm? Okay. Okay. Can you all view? Can you all view the screen? Participants?
Yes, ma'am.
Yes, okay. So now this is the main program, that is the PSO based optimization of manufacturing problem. So here the fitness function, that is the fitness function, which is the file name, which includes the program for all the program for the fitness function is included, and I initialize the number of variables for each particle as 6, and then the lower bound and upper bounds of the 6 variables are defined here and initialized here, and then the population size is also initialized, and this is the sub program I written it for returning the optimal solution. After calculating the optimal values, then it will return to the main program here. Here afterwards I will show it what is the sub program, what are all the sub program I developed. Okay, and this is the evaluation of the fitness function, where all this X represents the solution. Here the solution means which is nothing but the optimal solution. So here the 6 variables are in the form of defined in the range of a normalized values of minus 2.378 to plus 2.378, and this is the fitness function, that is the objective function of the welding problem. That is, this is the mathematical model for estimating the fitness value here. And this is the conversion of the decoded values that we mentioned, that initialized here. And these are the actual ranges of each variable that we initialize. And these two are the function program that is used for converting the normalized values to the actual range. That is, after obtaining the optimum, after obtaining the global best solution, then these values, it must be encoded from the normalized into an actual value here. So this is the function used for converting the normalized values into the actual range here. So now let me see that how it executes the program and what is the fitness that we are going to get in this program here. So here for number iteration, can you all see that? Can you all view that? Can you all view?
Yes, ma'am.
Yes, ma'am.
Yes, okay. Now I am executing the program. Here the iteration number 1. Here the global best fitness is 345.8, and the corresponding global best particles are 0.65 minus 1.22, 1.7, 0.07, 0.59, and minus 0.6 here. So here it is the fitness value is 345.8. So here it starts from here. It is there, the fitness point. So at iteration number 2, it's very clear. Okay. Now iteration number 2, the fitness value is updated. That is, the fitness value is updated from 345 to 356. That is 345 to 356 at the end of the second iteration. That is, the x-axis, it represents the iteration, and then the y-axis, it represents the fitness value here. So at iteration number 2, here the fitness value is updated as 356.4 here. And then iteration number 3. Again, iteration number 3 is, it is updated as 356.43, no change at all. Okay. And then iteration number 4, again, there is no change. Sorry, there is a change. It is updated as 357.58. And then iteration number 5, there is no change, remain as it is. And then iteration number 6, again it is no change, 357.5, slightly change. And then iteration number 7, no change, 357.5 remain as it is. And then iteration number 8, there is a change in the fitness value. It is updated as 362.1. And then iteration number 9, 362.15. Iteration number 10, 362.15. After that, it continues. So here, at the end of the 77th iteration, so at the end of the 77 iterations, here the algorithm is converged and the global best is considered as 377.52. That is, the global best is considered as 377.52. That is, the x-axis, that is, the iteration is 76th iterations, and the fitness value is 374.3, and the corresponding particle positions are corresponding optimal solutions are nothing but 1539.6 for the tool rotational speed, and 83.9 for the welding speed, and 9.1 for the axial force, and 16.5 for the shoulder diameter, and 5.1 for the pin diameter, and 508.6 for the last variable, tool material hardness here. So here, now we have the question, ma'am, we already chosen the iteration number as 100, but we got only the, at the end of the, we got the global best at the end of the 77th iteration itself. Okay, so already I told you, that is, the convergence of the algorithm based on two criteria. That is, for one way is to run the algorithm for a specific number of iterations, say 50 iterations or 100 iterations here. So at the end of the 50, the solution that corresponding to the global best is considered as the optimum solution. At the 50th iteration or 100th iteration is considered, and print the results and stop the algorithm. This is one way to stop the program here. And the other way is to stop the algorithm if there is no change in the global best value for at least 20 iterations or 30 iterations or 40 iterations here. Okay, where this program, this welding program, it belongs to the second criteria. Whereas here in this welding problem, what we have chosen, the maximum number of iterations for convergence of the algorithm is 100 here. But here when we are running the program, here at the end of the 77th iterations, we got the maximum fitness, that is the global best value as 377.52. That is the maximum fitness value of the welding sample here. Okay. And this is the main program. So here where this one is the sub program to find the fitness value here, initialized all the variables, and this is the developed function, and this is written as the fitness program. After calculating the result, then it will return the optimal solution to the main program here. So this one is the main program, and where the remaining things are all the sub programs, I written it separately here, and then I call by the main program. Okay. So now, to this in this welding program, I have developed the code and executed the program and exhibited the results also. That you got the fitness value as 374.89 at the end of the 77th iterations here. So in this lecture, I have given a general introduction to evolutionary algorithms in general, and narrated their advantages over conventional optimization approaches, and then described one of the evolutionary algorithms such as particle swarm optimization, and described the solution process in solving the simple welding optimization problems here. So the optimization is a simple one, and it is robust one, and it can be used by anyone without needing any theoretical background about the optimization theory here, and it can be used to solve the problems which cannot be solved by the traditional approaches. Okay, thank you for your patience of listening. If there is any queries, you can clarify.
Yeah, ma'am, I am having a question to you.
Thank you, ma'am. Now the participants can clarify your queries.
Am I taking too much of time?
No, ma'am. No, ma'am.
Oh, okay, no problem.
Ma'am, I'm having a question. You taken the particle swarm method. and
yeah.
what is the prime objective of this method, and what are the considerations we have to take
Fine
while I am doing
objective.
an experiment?
Yes.
Yeah, what's the prime objective? Because in particle swarm method, we are having lot of iteration values. Okay,
Yes. Okay.
a huge amount of population we are dealing with. Then,
Yes.
then how it relates with the source by using it?
Relate with the source means?
Source means what are if I am taking a welding program, the source is the heat generation. Okay,
So
so how it relates with that?
you can optimize either maximizing the losses
Ma'am,
or
regarding optimization, I'm not asking the optimization. Optimization is the better. I need to get a better value from out of this population. Okay, that is the final thing I need to know. Okay, what I'm asking is if I'm having a huge number of population, unknown population. Okay, unknown population means we are iterating in a virtual manner only. We are not taking an actual experiments. Okay, actual experiment. So my question is nothing but what is the actual objective of particle swarm method? Because lot of methods are available for optimization. Okay, fuzzy logic and lot of methods are available. Why beyond that nowadays particle swarm method is a very good one. I need to know why we are going for that.
It is simple. It is simple compared to the other algorithms. It can handle both the fitness function and the cost function.
Good afternoon, ma'am.
Yes.
Ma'am, this tensile test can be compared with practical experimentation, ma'am.
Yes, if you have the real-time data, then you can compare.
Which experimentation?
If you want more accuracy, then you need to get the data in terms of 1,000 values, 1,000 samples. So if you have large data values, then you can get the accuracy of the tensile strength in more well.
Can't we get any practical data from central database, madam? That is from Indian welding.
I don't know much about that welding problem. So already my colleague Dr.S. Rajkumar done the experiments based on the welded samples. So I picked the data from that.
You have collected lots many of data, madam.
Only 25 data set. In that paper he collected the data only for the 52 welded samples. So I have taken only the 25 data sets.
We also can collect and we can extend the work, madam, with citing
Yes.
the initially.
Actually, if you want to optimize any parameter for maximizing the tensile strength, okay. So here in this lecture, I have considered 6 parameters for optimizing the objective function of the maximizing tensile strength. Suppose if you want to design, if you want to think of only the one parameter for maximizing the tensile strength, for example, if it is the rotational speed, okay. So then you have to experimentally do the welding for a number of samples with different rotational speeds. Then you have to measure the tensile strength for each sample. Then you do it for 1,000 samples here. Then only you will have 1,000 data set for developing the mathematical model, that is the regression model that relates the speed and tensile strength here. So if you need that fitness function for doing the optimization, then that function it can be represented as y equal to simple of f of x. Clear? Okay. So now treating that rotational speed itself as a particle and the developed function y equal to f of x as the fitness function, then you can apply any of the evolutionary algorithm, not only that PSO. If any of the algorithm is available, you have to choose the algorithm based on the type of parameters, type of the problem, what you develop the model. Based on all these things, then you can apply the algorithm. Or you can apply the PSO also to maximize the tensile strength.
Madam, for the same PSO, can we change any variable, any one of the variable, like voltage or current or something parameter?
You can include.
Madam, one more last thing, madam. In MATLAB, you got 377 as the global maximum.
Yes.
But in theoretically, we got 374, ma'am.
Where that theoretically it's 74, it's a random value. It's not a original value. So for this demonstration purpose, I formulated the table values here, where that table value is not exactly with the running program value here. Clear?
Even in that graph, ma'am, it had not exceeded 375. It is
Yes.
below 375, but in command window it is showing 377.
So that's why I told that 377 is a tentative value that I took for the theoretical purpose. But exactly when we running the program, we got that value. Again, when we run the program, then the fitness value may be changed. Usually, actually, there's all these evolutionary algorithms are stochastic models, stochastic optimization process here. That is, stochastic model means what? That I said earlier. This is based on the stochastic approaches here. What do you mean by that stochastic approach? Usually
Random.
Random. That is, if a problem is represented by a certain set of parameters, then there will be only one solution. That method is considered as a deterministic approach. Okay. For example, let us consider a simple linear problem. We often solve in the basic mathematics. For example, 2x1 plus 3x2 equal to 5, and then 3x1 plus 5x2 equal to 7 here. So if you solve this problem 100 times by any method, then the problem is only one solution. Then that model is said to be a deterministic approach. So if a problem or model represents a situation where some uncertainty is present or involving some kind of randomness, then that developed problem is known as the stochastic problem, and the method that finds the solution is the stochastic approach. For example, the model that involves the rainfall forecasting, prediction, estimation, all these are all fall under the stochastic category here. On the other hand, all these stochastic models will likely produce different results every time when the model is done. For example, when we run the same welding program, welding problem, second times, again we'll get another fitness value as the global one. Okay.
Yes, madam.
It is not the constant value.
Yes, madam.
We are
Madam,
going
can we
we are
get
going to maximum value nearer to the global solution. That is the main objective of the optimization problems. Sorry, main objective of the evolutionary problems.
yes, madam. Madam,
Yes.
can we get MATLAB code for this, madam?
Okay, sure. I'll give it to your coordinator. He will send it to you.
Thank you, madam. Thank you very much.
Ma'am, I am having one more question to you.
Okay.
That means, so, ma'am, we are taking a lot of iterations. Okay, if I am taking the experimental value of 10 iteration, and the remaining I am doing in a virtual manner by using MATLAB, and how much we rely on that? How much we can relay? How much relay we have to give that virtual iteration values?
Virtual values.
Virtual means we are not conducting an experiment.
Okay, I know
Okay,
that.
we are not conducting an experiment.
Without doing anything, usually you can calculate all those values. So simple 10 iterations means the value will not be good.
Okay, ma'am. So, ma'am, we are doing, ma'am, you are giving an equation for that. For increasing the iteration value, you given an equation, isn't it? While you are presenting.
Yes. That
iteration number, we can go for the above 1,000 values by using that. Okay. So the values after the 10, it is we are getting an virtual values. That means the computer is generating the values according to the equation. According to the algorithm based. Okay. So how we can rely on that equation? Is it good or not? That I am asking. While we are doing a research, is it the values we are taking from that virtual manner? Is it really good or not?
My experience, the value is not good at that such iterations.
I couldn't get exactly.
Yes.
What you said, ma'am? Can you?
Yes.
Can you repeat it again? According to your view, what is the?
If you are taking more iterations, then the value will be a good optimum.
So by means of that, you are supporting that virtual values.
Yes,
if I am taking more and more.
More and more, then only you can get the good optimum solution. As the
okay, fine, ma'am. But I gone through a lot of research papers on that. It is showing lot of variation. the actual data and between the virtual iteration methods, there is a lot of variation of data. I am seeing that. Why it is cost then? Why this kind of things are coming? Because if you are, sir, your voice is breaking. Daskumar sir, your voice is breaking.
So Anish.
Yeah, okay,
Yes.
right now.
You are hearing my voice or not?
Yeah, okay.
Yeah. So normally the experimental value and predicted value is not more than 5% of error difference.
Okay, thank you. That is the right answer I needed. Okay, that is okay. That's a minimum
If
limit
it
and
is
maximum limit.
exceeded that 5%, that experimental procedure is wrong.
Okay, yeah, great answer.
So listen, usually we should not depend the paper values. Most of the times the values may be wrong. You have to do it experimentally and take the data.
Okay, ma'am. Yeah, it's a good answer from your side.
Consider all the data in the form of virtual way.
Okay,
Because
ma'am.
you can't get the clear final result.
Okay,
So,
nice.
if you are doing the research in this, don't consider the data set whatever obtained in the paper. Better you can do the experimentally and take the.
Actually, I am doing the validation of this data. So, okay.
What we have discussed now. Okay.
Okay, thank you, ma'am. Thank you so much.
Okay.
Any questions from participants?
Sir, there are no more questions in the chat box, sir. Can we close it, sir?
Yeah, tell me.
Madam, this is Subbareddy from the B.H.E.L College of Engineering.
I couldn't clear your voice.
Madam, this is Subbareddy from the B.H.E.L College of Engineering, Mayalaram.
Yeah, okay.
We have different optimization techniques.
Yeah.
We will be using ANOVA and response surface methodology and all these things. What is the unique feature of this particle swarm optimization, and what are the advantages? Where do we find advantages if we use other?
Unique advantage of all these evolutionary algorithms is no need to give the initial starting solution. Okay. Whereas in the conventional optimization approaches, in traditional algorithms, we have to give the initial starting value. Okay. So, but in these evolutionary algorithms, no need to give the initial starting solution, and they will give the global best solution. That is, they land at the global best or nearly the global best solution, and they do not require both the objective functions and constraints to be differentiable and continuous. And these functions may also be discontinuous and non-differentiable, whereas the classical approaches, they require all these functions to be differentiable and continuous as they compute the derivatives during the solution process. So for all these aspects, we consider the evolutionary algorithms are far better than the traditional approaches. And also, in addition to that, the maximum possibility of landing onto the global best is maximum in these evolutionary algorithms. For example, if the population size is 50, okay, so the traditional algorithm, it starts with a single initial solution point, and they perform a single iterative search for obtaining the optimum solution. But in such case, it reaches the suboptimal solution, which is not the good one here. But in case of evolutionary algorithms, if the population size is 50 mean, 50 initial solution points are randomly generated in the entire search space, and they perform the multiple iterative search for adjusting these solution points for obtaining the better solution. That is, the probability of landing onto the global best is 50 times better than that of the traditional algorithm that we started with a single solution point. Okay.
And can we find the interaction effect of variables, madam?
Yeah, I can't clear your voice, Pa.
Can we find the interaction effect, madam? Interaction effect of variables. Interaction effect.
I don't know.
See, if it's evolutionary algorithm, you are not getting any interaction effect. If you go for the design of experiments or response surface methodology or any statistical approach, you will get the interaction effect.
Okay.
This evolution algorithm only you will get the best optimal solution for your process parameter.
Yes.
Thank you, sir. Thank you, madam.
Okay. Okay.
If there is no questions, we will close it today. So first of all, I would like to thank Madam for taking much more time. So giving best lecture to this forum. So on behalf of the Department of Manufacturing Engineering, I would like to once again I thank Dr. Sasikala Madam for enlightening a nice lecture on the young buddies, maybe in their research scholars, maybe they will future they can use for the PS algorithm in their research work. Thank you, Madam. So once again, I will thank you. Thank you.
Thank you, Rajkumar. I thank the organizing committee also for having given me this opportunity to give a lecture to share this session. Okay. Thank you all. Thank you. Thank you.